Good morning. We resume today. It's a pleasure to introduce for the conclusion Professor Franco Flandoli from the Scuola Normale Superiore, still regularization by noise for ODEs.
Thank you very much. Let's see the plan of this last lecture. I decided not to give my impression on links, but only to speak of them, not of the links, speak of the topics, and then I hope that your imagination is better than mine, because more I think to them, more I get confused, and probably it's also because I'm a little bit tired, a lot of things to do in this week, etc. So, but the aim at the end would be to think if there is some common theory in which fluids in which dissipation due to small-scale noise, special phenomena opposite in a sense to dissipation, or including dissipation, again due to small scales by convex integration, and intrinsic stochasticity that I will describe by a picture is again a phenomena which could grow up from the small scales. They could have something in common. Okay, and what we have seen in the talks is that if we use a transport noise of a non-trivial type, quite elaborated, small scale, this provokes dissipation for certain problems like the 3D Navier-Stokes, sometime with due limitation that I described, some kind of no blow-up. And today I would go back just for 3-4 slides or less on the conditions of dissipation that I showed yesterday, to see that there is a detail which is different from those, for instance, of convex integration and other theories. And so I want to emphasize that. Then I will move to a sort of introduction to convex integration, even if I'm not an expert, and then just one slide with a picture about intrinsic stochasticity. Yesterday we have seen this two-dimensional Euler equation with this transport noise, rewritten here, the noise, the coefficient sigma k, the covariance, and the formulation. You remember the original formulation as a Stratonovich noise, and when Stratonovich is rewritten as Ito, appears this corrector, the corrector of Ito Stratonovich. Which is an additional dissipation in principle if the noise is small, and the noise is controlled by a constant, is small if this constant is small, and this constant is related to this quadratic form, the quadratic form of the covariance. Still, we want that the covariance on the diagonal is large, not infinitesimal, but we would like that the covariance in the two variables integrated this way is small. And we have seen conditions under which this was true. Just let me remind, we don't need these details now, just remind that if we take the sigma k that are rapidly oscillating, rapidly is because the wave numbers k are of the order of some small length scale, Ln is a small length scale, Ln minus 1 is large, so we have large wave numbers in these exponentials, and the size of the sigma k is small because there is this square root of length scale. And this nu t, which will have the meaning of turbulent viscosity, t is not a time, there was a misunderstanding yesterday, t is not time, just the usual notation in turbulence theory for the turbulent viscosity to distinguish from the other viscosity. This is given in a sense, or if you build a model with physical meaning, you find a nu t. For me, mathematics, I prescribe a nu t and I construct a model which produces this nu t. And indeed, the qxx, the diagonal, is proportional to nu t times the identity, and the constant is small, like the length scale. This we have seen yesterday. But I want to see what happens if we use wave numbers like these ones, that I will go back to these ones in the convex integration, in contrast to those written here. Here you see I take all wave numbers, all wave numbers that have a certain scale. So there is the origin and a very large, I take all wave numbers at this level. Here I could play something different. I could say, the picture maybe is small. It's not visible that the length is 5. Okay? Because this vector is 0, 5, and this is 5, 0. Okay? And so we have this 5 here, with only 8 vectors. And we could expand them to a larger, but what we expand, what we get, what we expand? We expand, one vector is expanded here, so one is here, another is here, another is here, another is here, another 2 here, and opposite. They are perfectly fine to build up a diagonal which is identity, because in order to have the identity, it's sufficient to take this one and this one. You take this tensor product, you get an identity. If you have 8, you get 4 identity, 4 times the identity. Yes, but this is not good with respect to the previous picture in which we use all of them. You will see why. Because when we do, so if I compute if I take only, so let me be precise. I take only the sigma k with the same shape as in the previous slide, but only with the wave numbers, these 8 wave numbers, not all of them. Then I put a weight theta n in front. Before, you remember that the weight was very special, square root of a certain length scale nu t. Now I look for a weight which works. Okay, so theta n to see if it works or not. And this ln, this distance is still ln minus 1. You see it here. It's not very visible, but you see it here. Then we computed the diagonal. Please believe that the computation is correct. You find theta n square times 4 identity. And then you compute the quadratic form. Please jump the computation. Please believe that the computation is correct. You find that the epsilon is theta n square. So there is no way to keep this non-zero and to send this to 0. And this is completely different from, for instance, homogenization, also from convex integration, but also from homogenization, in which you have a field and you rescale that field. So you have a field with some level of complexity and rescale the field. Here is different. When I rescale, when I move to large wave numbers, I take more fields. It's like to say that when I rescale, I change also this field, taking also many more directions in this field before I rescale, and so on. And if I rescale more, I take a more complex field. And this is what I did here. So in this theory of dissipation by noise or regularization by noise, we do something about the complexity of the fields, which is not typical in other areas of mathematics. Okay, and it's not very visible a priori. It took me quite a lot to realize that there was this difference. I didn't realize immediately. My student know, because we discussed this year after a lot of time in which we had in mind these ideas. And here I just, this is about homogenization. This slide is not important, but just to say, if you take the classical framework of the so-called diffusion approximation, so a first-order differential differential equation with rapidly oscillating fields, the rescale of a given field, under certain assumption, it converges to the heat equation with a constant k, but the given field is a single one which is rescaled, opposite to what I showed above. Okay, and now this was a remark, just to say that we need that complexity in the stochastic theory. Now, a few words about convex integration. I already said that I'm not expert at all. I ran a working group in the last 2 weeks in France of physicists. These are young physicists. Okay, Rick Simoneno is not so young, but the other are very young physicists that in a summer school in theoretical physics. And with this small group, we wanted to do a numerical exploration of convex integration. At the end of 2 weeks, we just understood few lines of the papers of convex integration and did a very poor numerical simulation. So we will continue in the next month. So I don't have beautiful results on the numerics. The numerics is extremely difficult. There is an expert in Japan, Matsumoto, who tried to do the numerics of three-dimensional convex integration, and after 3 iterations I had to stop because the scales reached the level of, he's an expert of direct numerical simulation of 3D Navier-Stokes, so he knows how to handle the best possible supercomputers for 3D Navier-Stokes, and after 3 iterations it was off. I mean, the complexity was already too much. And so our purpose was to do in 2D, in 2 dimensions. And in 2 dimensions, so we wanted to be very concrete, and Ciro Campolina, as I already said in the other slides, devised the concretely vectors that works for the so-called Nash lemma that I will recall below. So these are the 8 vectors which are sufficient to put in practice the so-called Nash lemma. They are not so visible. It's important to say that the length is 5 and they are carefully chosen. Nash lemma is this theorem, or lemma, that says the following. But I write the Nash lemma in the particular case that Campolina developed is not published. I mean, it's an exercise. I mean, we had in mind the general lemma, and reading papers, etc. We found a concrete version, but he found this concrete version. So call sigma 0 the set of those 8 vectors, okay, that I showed several times. So sigma 0 are these 8 vectors. And so the wave numbers k0, I put 0 to remember that they are small, they are not large. So k0 are small wave numbers, length 5, belonging to this particular set of 8 vectors. There are 8 functions, gamma, k. They are functions with the domain, but the domain is clear from what I write below, with the following properties. They are functions of tensors, 2x2 symmetric matrices. So if I take a 2 times 2 symmetric matrix, I take a null trace, but this is optional. These matrices are 0, the 0 stands for null trace, should be close to 0. So that identity plus this matrix is close to identity. When you read the classical version of Nash lemma, you always read a matrix R which belongs to the ball around the identity with some radius R0. I reformulate, since there is an R close to identity, and R0, which is small, to avoid confusion in the talk is short, I decided to avoid this notation of the classical theory and speak of identity plus a small matrix. So the lemma of Nash says that if you take matrices close to identity, symmetric, sufficiently close to identity, close, since we are in a concrete example, precisely means that each entries of R0 do not exceed 1/3. So if if you write the entries of R0, they are all smaller than 1/3. And so identity plus such matrix is represented by means of this particular matrices, identity minus tensor product of the 8 components. Of course, you need coefficients. The coefficients should depend on the matrix you want to represent, and these coefficients are smooth functions, even without the square. Namely, these coefficients are smooth functions, and in the representation you have the square, which is positive, of these coefficients. And these coefficients are very concrete in the example. The gamma square are a linear combination of the entries. So you take the entries of identity plus R0, and you make a linear combination of the entries. When you take a square root, apparently you would say, if I take square root, there is a square root which has a singularity. Yes, but due to the fact that the coefficients are have a bound, are limited to some range, here you compute the square root of a quantity which is never close to 0. So this is a smooth function also taking the square root. Okay, and so Nash lemma, which is probably cleaner if I state it in the classical abstract way, in fact has very concrete reformulations in R2. In R3 there is an analogous formulation, but the number of vectors is not 8 but much larger. Okay, the classical estimate is 90 something, and there are conjectures that can be put down to 16 perhaps, but it's not very clear. So dimension 3 is more complicated, but dimension 2 is very concrete, and this is Nash lemma. Nash lemma, conceptually, apart from detail, is representation of tensors, general tensors, by means of special tensors made with special directions. Okay? And there is a twin, oops, I used only one finger, so I don't understand why I make this mistake. Okay, let's do here again, and let me try again. Okay, so this is Nash lemma. I want to reproduce the same kind of right-hand side, by a completely different computation based on vector fields and integrals over the torus of vector fields. So I move from linear algebra to analysis, vector fields, and I want to do a computation which produces precisely the same result. And so the logic will be that by means of vector fields I can reproduce matrices. I want to reproduce matrices by means of vector fields instead than using matrices themselves. And so this is a very beautiful part of the theory of convex integration. I use these vectors. K0 is one of these 8 directions, and the usual complex exponential. With this perp, you know that the divergence is 0. Not only, but it is also a stationary solution of Euler equation without pressure. Is a shear flow indeed. Particular shear flow, but it is also the Fourier basis of the space of divergence-free fields. They are clearly inspired to three-dimensional Beltrami flows. Beltrami flows are very similar, except for the fact that the property that gives the name Beltrami to a fluid flow is that vorticity and velocity have the same direction, are aligned. And in 2 dimensions, this is impossible by definition, because velocity is in the plane of the fluid and vorticity is perpendicular, so they are never aligned. So Beltrami flow in 2D is meaningless by definition, but the shape of these fields is the same as the shape of 3-dimensional Beltrami flows. I will make remarks about Mikado later on. And then we take linear combinations of these fields with particular properties of the coefficients to have these combinations real valued. What is not obvious a priori is that if we take linear combinations of solutions of Euler equation, it is again a solution, because of course Euler equation is not linear. So it's not obvious a priori, but it is true for certain fields, in particular for Beltrami, Mikado in 3D, and for these fields in 2D. Maybe others, but these are very simple oscillatory fields in 2D, which have the property that the sum remains solution. You have to tune certain facts. I mean, it's important the shape of these 8 wave numbers have been chosen carefully in order to have this property. It's not obvious. It is due to, you can find the proof in a paper, in this paper, that if you take these linear combinations, they are divergence-free, because divergence is linear, but they are also solution of the quadratic Euler equation. With some, there is a pressure. For the simplicity of exposition, I don't write the explicit form of the pressure. Okay, the explicit form of the pressure is very important in some detail that I completely put under the carpet. Okay, so please accept that in the time, in a reasonable time, is impossible to give all the details. So the pressure, which is important, is put like generic pressure. There is another detail, very, very important. This average, by this notation, let me change the color. Oops. Non vuole cambiare il colore. Okay. So let me say that this notation stands for the integral over the torus. Okay, the average, because since I was in a school of physicists, of course they wrote like that, the average. So if you take the average of V tensor V, this V, you get the same expression that you remember was on one side of Nash lemma. And these computations are not trivial, but please accept them as a result. And similar properties, this set of properties up to details, are true for in 3 dimensions for Beltrami and Mikado, and in 2 dimensions for these fields. Mikado, they even have 0 pressure. In 2D, unfortunately, you know the Mikado that are tubes, little jets, velocity jets. In 3D, you can build them in a way that they don't intersect. When you project to 2 dimensions the same concept, they necessarily intersect. Unfortunately, the intersection is not small, and it violates the properties. When you do the computation, the intersection appears on the other side. And so these properties are made dirty by the intersections in 2D, which doesn't mean that they don't work. With suitable corrections, maybe they work. But in particular, you described intermittent Mikado flows, etc., that could work in different cases. There is a recent paper in the two-dimensional case using intermittent Mikado flows. So there are many possibilities. Let's say this is true for two-dimensional, let me call Beltrami flows, or in 3D for many other cases. And so you remember there was this property for matrices. A matrix is represented in this way, and similarly the average of this tensor product produces a similar expression. And so now we merge these two in the following way. We take a tensor depending on x and t. Before, the tensor in Nash lemma was a given tensor. Now is a function of x and t. And since I have to use the infinity norm in space-time, time is on a bounded interval and x on the torus. So infinity norm of this several times. Unfortunately, maybe I used the wrong symbols of tech, but it's too big, this. I decided to shorten like that. So remember that R infinity means the infinity norm of this, otherwise formula blows up. And then I take a field which is a combination, is like before, a linear combination of the elementary, let me call two-dimensional Beltrami, if they are not Beltrami. Linear combination of the two-dimensional Beltrami. The coefficients are the gamma of Nash lemma. In Nash lemma, there exists this gamma, which are very concrete, but there exists this gamma. So the coefficient of the gamma of the Nash lemma computed over identity plus something small. This R0 maybe is already small, but in case it's not small, we divide by its infinity norm and by 3. So this object has entries which are smaller than 1/3, and so it satisfies Nash lemma. I can put inside and have that an expression like that, an expression you see here. Nash lemma says that the sum of gamma square of this object, thanks to the fact that this is smaller than 1/3, times this vector is equal to this object itself, which is here, to this object itself. So if you take this gamma square combination of this object, you get the same object. Then there is this factor in front which makes readability a little bit less clear. There is a detail in this definition that we have to adapt to the notations. I introduce a vector field with two space components like we do in multiscale analysis. Later on, this xi will be lambda times x with a suitable choice of lambda. But for the time being, it's good to keep the notation separated. So the Beltrami flow have the variable xi, and the variables x and t of the original tensor are these ones. There is a factor, a constant. This is just a constant in front, which appears because when we do w tensor w, it is a square, so this square root becomes this, and so there is this constant everywhere in front. Okay? So now which properties I have used? Here I have used the property of this combination of vector fields. This combination of vector fields in the variable xi satisfies, you remember, the two properties written here. Solution of Euler equation and average equal to that. And so the average in xi, in the variable xi, is equal to that. but that by Nash lemma is equal to the matrix times this small constant. The small constant is important now because becomes the small constant against the identity, which will be absolutely unessential. So you can forget about this factor. But very important, we have reconstructed the tensor depending on x and time. So the tensor depending on x and time is represented as the average with respect to this second parameter of these particular vector fields. These are preliminary fundamental informations of the theory of convex integration. Since, at least for me, this is very difficult, I will summarize more than once what we have done. So first, the summary. We have introduced a special set of wave numbers, but limited, eight wave numbers. Special functions of matrices. This is Nash lemma. Special fields inspired to Beltrami flows, and using these special fields that by themselves are solution of Euler, we construct other solutions of Euler, solutions in the psi variable, which are linear combination of this one. It's very strange that linear combination has this solution, but it works for these very special fields. The linear combination, the coefficients of the linear combinations are taken from Nash lemma, are the gamma k of Nash lemma, computed over a special cooking of a tensor given a priori. You will see why in the so-called Nash iteration that was already introduced yesterday, and I will recall, there is in the steps of this Nash iteration, there is a tensor R. We want to update the tensor R, so we use the tensor R to build new fields, and with these new fields we update to a new tensor R. Okay, so the old tensor R enters these coefficients. These fields, I'm summarizing, these fields satisfy Euler equation, and the averaging psi of these fields reproduces this tensor up to something absolutely not important. I anticipate, because to understand the things, that later on I take this field with the variable psi equal lambda x and construct a field which is only function of x and t, like in multiscale analysis. Now we need another very important remark. Recall this complicated formula and recall this average property. Now we need a property which links this tensor product to R0 without the average. This is a little bit strange a priori, because with the average the link is clean. The average is equal to the tensor up to. Without the average is not equal to the tensor. But if we develop Fourier analysis in psi, so x and t are parameters now. Develop in Fourier this, on the torus, this tensor, each component of the tensor, take each component of the tensor, develop in Fourier. They have a constant term, which is this average. So the average is the constant term, plus a sum of other frequencies. But these frequencies have two very important properties. The first is that these frequencies that I call K1 because is again a few ones, very limited, is not something that goes to infinity. These frequencies belongs to a finite set F1. In fact, these frequencies are just some. You have to think what happens when you do the tensor product and you take two components. When you do the tensor product, you replicate these exponentials twice with two different values of K0. Since the set of K0, if there is a K0 here, there is also a K0 there, you produce a constant term. All the other, if you mix this with another, the exponential part does not disappear and produces a K1. And so there are a finite number of this K1. And this set F0 is written perhaps somewhere already here. This set F1 does not contain 0. So these wave numbers are not 0 because the 0 wave number is already there. And this is extremely important. So even if this relation is not clean, it's extremely important. Even without the average index I variable, this tensor product is equal to this tensor that in the iteration of Nash is given, plus very oscillating fields, all of them oscillating because the 0 frequency does not belong to this set. Very oscillating fields. So in a sense, we have reproduced the previous tensor by means of a tensor product of new object up to very oscillating fields. If you want, maybe the picture that I'm going to do is not completely correct, but this is my mental picture of R0 as a function of x and also of time. And this is my picture of this tensor product, of the tensor product without the average. So this tensor product, locally, it averages to R0 as very high frequent oscillations. In the average is R0, but has very high oscillations. If you see this picture, you say, yes, but I expected a small object. The smallness, okay, the smallness is here, but you see, if R infinity, which is this, is the infinity norm of this, is small, then this is small. The degree of smallness of this oscillation is precisely the same degree of smallness of this one. Now there is another ingredient which reduces the size of this enormously, is absolutely genial. So it's not finished. The number of ideas is not finished. So until now we have reproduced a given tensor in two ways, either by the average in a very precise way, or by oscillations in a up to in this way. Now there is the last fundamental idea, but probably I summarized because of the complexity. What we need to know is that we have constructed a field with two space variables that later will collapse in one space variable, solution of Euler with the average precisely equal to a given tensor and without the average given by the given tensor plus fast oscillations. Before I introduce the last incredible idea, the Nash, let me recall the Nash iteration. The Nash iteration is the following. In the iteration at level Q, we have a solution of Euler equation, Euler-Reynolds, so to speak, Euler-Reynolds. And we want to construct a new solution of Euler-Reynolds. Of course, using the previous one and some trick, but with the following properties that I write in a very heuristic way. If you read the papers, it's always written, this is less or equal than lambda q to the power beta, etc. So, of course, this is a short talk, so let me just say that we want that the solution U of the new iteration with respect to the previous one, the difference is very small. So the idea is we start at the iteration 0, at the beginning of the iteration, with a u. And then we want to change it very, very little, very little. So the difference is very small of the changes. At the same time, we start at time 0, at iteration 0 with an r which is not so small, and we want to reduce very much during the iteration. So at the end, this probably is written in the next slide. If we succeed to do that, at the end, the R will disappear. If these are small enough, the series converges, and total convergence of the series. Sorry, I noticed now the topology. I did everything in the infinite topology, but of course the advanced theories use Hölder topology, and so the final total convergence is in better topologies, and the final solution, as you know nowadays, is Hölder up to 1/3 excluded. I just, for simplicity of notation, use the infinity norm. So by this, you converge at the end to a solution given by the sum of all these iterations. This will be a solution equal, to 0. To 0, because the other terms goes to 0, is the divergence of, but in weak sense it goes to 0. Okay. And if we have cooked the first iteration, U0, the first iteration, in such a way that it is strange, then we try to preserve this strangeness in the limit. Okay, something like that. From initial condition 0, we construct a solution that is not 0 without any forcing term. This is the iteration strategy of Nash, but then now in the iteration we put the elements that we have understood, and so I have to explain how to construct the next iteration given the previous one. So you see there is an RQ given, and I have to elaborate this RQ to construct the RQ plus 1. And recall that the infinity norm is shortened, but now there is another symbol Q, so it becomes RQ infinity. RQ infinity means the infinity norm of RQ. Very good. Now I have to play, because otherwise it's clear that the construction is too difficult for a talk. And I play the following way. I give only a crude approximation of the next iteration. A crude approximation which, in my opinion, captures the first important philosophy before you make suitable corrections to this philosophy. Okay? So I give only a crude approximation of the true next step. Okay? Keep in mind that it is not the correct object, the one I introduced. The crude approximation is made of, I have to say, what is UQ plus 1 first. UQ plus 1 will be UQ plus a vector field. And essentially the vector field is the one I write here. In the next slide, certainly I've written that UQ plus 1 is UQ, the previous, plus this new vector field. This new vector field in which the xi variable is lambda of x, a suitable lambda. But first let us see again what is this vector field. This vector field Q plus 1 is our old friend. So linear combination of Beltrami flow with the Nash coefficient adapted to the RQ of the previous iteration. I already explained, but here you see it clearly written with the infinity norm in the right positions. And so remember that this satisfies with the average. The average deletes all frequencies which have non-zero k and remains this object. Otherwise, there are these highly oscillating parts. Highly oscillating. They are not already highly oscillating because there is the variable psi. But then, when now in place of psi I put lambda, so in place of psi, now I put lambda x, so with large lambda, so they become highly oscillating. And the lambda is adapted to the iteration, so is a lambda that we call Q plus 1. Okay? And so this is what we read in the next slide. We read that we take this vector field lambda q plus 1x and we add to the previous to get the next. And now comes something that I hope that the experts of convex integration don't kill me. I give you the RQ plus 1. Because in all papers the RQ plus 1 is implicitly defined, is the solution of the divergence problem, which exists, it has very beautiful bounds, etc., but it's not very visible what it is unless you read the proof. And this formula is a sort of first approximation of the true one. And I like it very much because it gives the impression of what is the next RQ plus 1. First, there is a notation here that I forgot to emphasize in the previous slide. When we are at level Q plus 1, this tensor product is equal to its average plus this oscillating field, and of course I denoted by A Q the coefficients of these oscillating fields. The choice of this Q is not only notational, is to, in a sense, to remember that these fields in the variable x oscillate at the previous level, so to speak. You have to see the construction to be sure of that, but the psi will oscillate much faster, but the coefficients oscillate at the same level as this one. So this one, like this coefficient, are slowly oscillating. The next, the psi is rapidly oscillating. These terms are rapidly oscillating, okay? And so the new Q plus 1 is the following object. It contains the divergence of those coefficients. It contains the sort of analog, at least the complex exponential with the lambda Q plus 1 x, so very rapidly oscillating. But the key point is that it contains this factor. This factor was not in the previous expressions. The previous expressions, nowhere you find this factor in front. You find always this boring factor 3R0, 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 but you never find this factor. This is the fundamental last idea, and is the property of the divergence operator. So this is the key property of the fact that we want to solve div R0 Q plus 1 equal to something. The div kills, if you do the inverse of the div, you gain such a factor. But not always. You gain such factor if you apply the inverse of div to oscillations that contain this factor. If you apply the inverse of div to a constant term, you don't get this constant or slowly varying term, you don't get this factor. You get this factor only if you apply to fast oscillating terms. And this is the secret of the last step. So please take this definition. We define R0 Q plus 1 this way, and let us check that they work. Let us check that together they almost satisfy Euler equation and also satisfy the smallness that was required. First, the smallness, which is easier. You remember we wanted that the infinity norm at the iteration Q plus 1 is much smaller than the infinity norm of the previous iteration for R. And where does it come from? Of course it comes from this factor 1 over lambda Q plus 1, but pay attention, there is a problem. Try to prove this inequality. This factor is here. This RQ infinity is here. These are bounded by a constant, by 1 or by a constant, but the problem is that there is the divergence in x of this factor. But you remember I said that this factor oscillates at level lambda q. slower oscillations, and so we pay a factor lambda q above. But then, when we choose the sequence of lambda q in a suitable way, of course, we make this ratio as small as we want. And so we gain from that. Concerning the smallness, this is a rewriting of the smallness of u q plus 1 minus uq. Infinity no. You remember that we start from a u0 and we want to deform it very little with iterates. This this is precisely w, okay, by definition. Precisely up to some approximation that I'm doing. This w from where is not in this slide. So how to prove this bound? Simply I have to go back to the previous slide. If you take this w and you estimate the infinity norm, there is this constant. These functions of the Nash lemma, if you see again the expression, are square root of numbers in a small interval, so it's nothing, and this is nothing. So essentially it is this constant up to the multiplicity of this sum, which is fine, up to a constant. And so the size of the w, sorry, it's moving too fast. Let me redo. The size of this w is bounded by the square root of R0. There is a misunderstanding sometimes for people like me that read the paper the first time. We tend to think that when we move from iterate q to iterate q plus 1, we gain smallness of everything. Okay, the rq plus 1 is much smaller than the previous, but the wq plus 1 is not much smaller than the previous. It is of the same order of the previous, precisely with the square root, because you remember that r is related to the square of this. So the size of the smallness of this is the same smallness of the previous one. Anyway, in the iterations, these are smaller and smaller, and so these also are smaller and smaller. Okay? So smaller they are, but this is really super small. This is not super small. Okay? Numerically, this may count. may count. Okay. Here I wrote. Recall that the wq plus 1 was square root of this times an essential object, so this is clear. So the smallness is clear. What is slightly more difficult, but very beautiful, very elegant, is that they solve the Euler-Reynolds equation, approximately. This is there is at least one very elegant step in this verification. So here I jumped to maintain 24 slides. I jumped a detail. So the previous iterates are Q and UQ satisfy Euler-Reynolds. The next should satisfy Euler-Reynolds. If you subtract and make a manipulation, you find a new equation which is satisfied by W, by the W, and by the other objects. It's clear. You have two equations. You say, but what W should satisfy? And so you write an identity which should be satisfied by the new R and the W. These algebraic steps I jumped. They are an extremely easy exercise. So please believe that from the two Euler-Reynolds equation, if you make easy manipulation, you arrive here. Let us read together this identity. It says that the divergence of the new Reynolds stress should be equal to the divergence of the old Reynolds stress modified by this tensor product plus some pressure. This pressure is not so obvious as I do, but I already said that I put under the carpet, plus two other terms. These two other terms are called transport and Nash error terms, and at least the transport is very non-trivial, very difficult. And so, in a sense, with respect to my presentation, this is the main point. If you want to move from my presentation to the true papers, the main effort is there. The other points, essentially, I did. But the main effort is to understand the term called the transport error term, which I miss. Forget about that. I have no way to contract everything in 1 hour and few minutes. And so, but also there is also another reason that I would say that up to something, all the ideas were due to this identity, this part of the identity. Then it's necessary to correct, and so there are new ideas. But most of the ideas are related to this identity. Okay? So, with the mind, please forget about these terms and think that up to approximation, what we want to check is that these are almost equal. I mean, we want to check in the sense that if you go to slides before, I defined W, I defined RQ plus 1, I checked that they are small, but I didn't check that they satisfy the equation. If they satisfy this identity, everything, the equation is satisfied. If they satisfy this identity, okay, there is an approximation. Okay, but I will limit myself to check that RQ plus 1 and WQ plus 1 satisfy this reduced identity. Okay, I hope you pardon me for this, this approximation. And so I have to compute the divergence of the new Reynolds stress and see what happens. Remember, this is the result and this is the reason. So remember that RQ plus 1 was defined in this way. That since the formula are long, I bore you by reading them again and again. So RQ plus 1 is composed of a finite sum of Beltrami flow of frequencies, multiplied by the divergence of those a little bit mysterious but coefficients, and multiplied by a constant and divided by lambda q plus 1. When I do the divergence in x of this, I have to differentiate the x here and the x here. I have to differentiate x twice. So usual rule of differentiation. When I differentiate this x, when I differentiate this term, I pay a factor lambda q, because you remember that these coefficients, like RQ itself, oscillate lambda q. So when I differentiate this, I pay lambda q. Is divided by lambda q plus 1. The ratio lambda q over lambda q plus 1 is very small. This term of the derivative is very small, is part of this almost equal. Then I differentiate in x here, and I produce exactly the factor lambda q, which cancels this one. And is this result. And is this result, because when I differentiate this lambda q, the lambda q goes down and cancels. And it remains precisely 3r, sum of the divergences, and this part disappears because when I differentiate this x, there is a factor k1 which goes down, contracts with this in value 1. So this, what I write here is the derivative with respect to this x, which is the one which counts. So until now we have understood that, and essentially I would say that inside here there is the deep, it's written here, there is the deep stationary phase lemma. So the deep stationary phase lemma, which is a lemma on the inverse of the divergence operator, essentially does what I explicitly did in this slide. So until now we have understood that the divergence of the new Reynolds stress is given by a certain expression. The next line we want to understand is that this expression is equal to this one. And this is just because we have to remind notations. Identities proved before. Let me, since questions the first time are very long, let me read. You remember that the vector field W that we constructed, if we don't take the average, is given by its average plus these rapidly oscillating fields. And therefore, if we take this object tensor itself with the xi variable, minus R0 with the x variable, and we take the divergence in x only, so not we do not take the divergence of W with respect to the xi variable. We just take the divergence in x of this tensor product in the x variable, minus R0 in x variable. And only later we replace xi equal to lambda x. If you do the divergence in the x variable of this minus this, if you take the divergence of this minus this in the x variable, this is a constant, it's a constant, the divergence of this is 0, is a tensor, but if you compute the divergence of this tensor is 0, and there remains the divergence in x of this, which is precisely this one, the divergence of this. So this term with this divergence is precisely this divergence. It's a very strange divergence. The divergence in x of the fields where I still keep the xi variable freezed and only I replace after computing the divergence. This is just a simple computation. The difficulty is just the time and the speed. But the next computation is extremely elegant. So until now we have proved that the divergence of the new Reynolds stress is the divergence in x of this tensor product with the xi variable, minus R0, and only later, after we compute the divergence, we replace the xi variable. I shorten this line in this notation. Okay? So this line is just this notation. And then I add 0. But what is this 0? Is the divergence of the same object in the xi variable. Multiplied by lambda. The divergence of this object in the xi variable is a gradient of a potential. I use here the fact that these vectors are solutions of Euler equation. Until now I have not used that. So I use only in this step the fact that the W vector field are solution of Euler equation to say that I can add plus 0 up to a gradient, to this computation. You understand why? Because divergence in x plus lambda divergence in c is the full divergence. So instead of this strange divergence in x later replaced, if I do this sum, I'm computing the full divergence by change of variable. The full divergence by change of variable is divergence in the first variable plus divergence in the second variable times the derivative of the second variable. This lambda is lambda q plus 1. Is this lambda q plus 1 which comes out from the derivative of the composition. And so, before we have proved that the divergence of the Reynolds stress was a partial part of this full divergence. The other partial part is 0, and so we can add and put them together. Essentially, I've used in essential way the fact that this divergence is this is a solution of Euler. So, for instance, if you use Mikado flow into D, these intersections produce a remainder, and these remainders, so assume that you try to play with a two-dimensional Mikado. Unfortunately, they have intersections, so due to the intersections, they do not satisfy precisely Euler equation, but there is a remainder. And then the remainder multiplies this huge number. So this is not zero, there is a remainder multiplying this huge number, and this spoils everything. So it's very important that this huge number is multiplied by zero in this kind of computation. And therefore, we summarize. I already said that the sum of these two divergences is the full divergence up to a gradient, but this was precisely what we wanted to check. Because of course, it is so fast that probably many of us, including myself, don't remember what we wanted to check. But what we wanted to check is this identity, that the divergence of the new Reynolds stress is equal to the divergence of the old modified by this tensor product up to a gradient of a potential. And we are done. So this is a strange presentation of convex integration because, okay, if you read the papers, you will find the differences with respect to this presentation. Okay, so I don't want to add special philosophical comments. Simply repeat what I would like that everybody try to get a picture. We have more or less the same models, but at the beginning, in my first lecture, I showed that they are not exactly the same, so there should be some research to unify. One model is Euler plus Euler-Reynolds, and the other model is the model in which I developed the dissipation by noise, which you remember is again a simplification of Euler, but of another type. So there are two slightly different simplifications of Euler equation in two different directions. In one direction, using exactly the Beltrami flows, but randomized, the effect is a decrease of energy. In this setup, using exactly the Beltrami flows, not randomized, and tuned in a very special way, we produce increase of energy. Okay, so it's necessary to understand what is going on. I think is almost the same model, almost the same small scale, rapidly fluctuating building blocks which enter the two models. One enter randomized, multiplied by plus minus 1. The other enters in an iterative way, very careful, not randomized, and produce opposite effects. So there could be many questions about this difference, but at least I wanted to say that these two theories speak of the same things. They don't speak of two completely different theories. They are almost the same problem understood with two different technologies. And the presentation that I did here is slightly different from those of the usual papers, in which I gave the definition of RQ plus 1. Usually RQ plus 1 is the solution of the divergence operator, a little bit mysterious. I gave the definition explicit of RQ plus 1, sum of certain things, is just to say, maybe in the future it's possible to play over that definition, which is concrete. For instance, multiplying this by plus minus 1, doing something to understand if we randomize this construction, what happens? What happens? If we modify this construction in a suitable way, what happens? Unfortunately, this construction starts from a given solution and produce this RQ plus 1 corresponding to a given solution. This is a big drawback. So it's not the philosophy of inserting into the equation small scales and see the effect. You start from the effect you want and you construct the small scales which produce your effect. But if things are sufficiently explicit, maybe it's possible to modify this small effect and see how they modify the big output that was chosen a priori. It was my dream, but until now I have not understood it. And intrinsic stochasticity. At the end, I decided that I will make a picture, but it's necessary that I change the colors. Okay. If I cannot change the... Capisci perché non riesco a cambiare il colore? Che con un colore solo non ce la faccio, non capisco. Ah, pigiavo la gomma. Sì. Santo cielo, che imbranato. Grazie mille. Ok, allora. So there is a large scale. To have a feeling, you can say that, let me check if I have time, in 5 minutes I conclude. 5 minuti vanno bene. Solo, this L can be 10 to the 3, so varese. And time scale is this number at power 2/3. So is 10 to the 2. These are meters and these are seconds. And in Varese there is a flow moving with this time scale. It moves at that space scale, and then you go down to another color. You go down to another scale. For instance, L to the 10 to the square, so this villa in meters, and time, 10 to the 4/3, so it's a little bit abstract, seconds, in which we can appreciate how the trees produce vortices, etc. And then clearly you go down, and simply let me go to the very small scale. Could be the so-called Kolmogorov scale. The Kolmogorov scale usually is like, let me write somewhere else, is like the viscosity to the power 3/4. The viscosity is roughly 10 to the -6. So let's say we arrive to 10 to the -5, so to speak, meters, with a time scale which is 10 to the -10/3 seconds. At this micro scale, there are microscopic vortices that we don't see, but they exist. And I heard from Alexei Malibayev that Landau-Lifshitz, sorry if it is wrongly written, wrote this equation. I knew, but I forgot it. Wrote this PDE. This PDE, Navier-Stokes, with additive noise. Additive noise in the following form: minus divergence of an artificial Reynolds stress, and with a coefficient in front. Sorry, it's beautiful that. Sorry, let me erase and rewrite, because the coefficient is very. No, I don't. Yes, the coefficient is beautiful. Is something like 10 to the -20. Very small coefficients in front. Minus divergence of the Reynolds stress, and the Reynolds stress. This Reynolds stress. Don't need to write here. Reynolds stress is space-time white noise. Space-time white noise. So first, I claimed sometime during the talk that additive noise is not good for regularization by noise. Maybe it's true, but perhaps it's something very deep, the additive noise, but extremely small. And this blue object I should have written here, because it works here. It works here. It's at the molecular. It's due to the molecular. This noise is due to the molecular level. Molecular level. This is molecular level, thermal noise. please don't ask me to defend this idea. It's written in Landau Lifshitz that they defend by themselves. So I cannot explain why they believe that there is such an extremely small thermal noise in Navier-Stokes and why it is important. But it seems that they claim that is important, and David Ruel tried to compute the effect of this noise on the Kolmogorov scale, on the smallest scale where we still appreciate vortices and below we don't appreciate anymore. And it seems that there is, in the opinion of Ruel, this thermal noise has an effect. Then from this upward is deterministic. So this is the picture that Alexei Malibayev taught us 1 week ago, in which, in his opinion, he's developing models, unfortunately not yet Navier-Stokes. These are artificial models in which he takes this limit, take the limit, these are a finite number of layers, take the limit to an infinite number of layers, so you send the viscosity to 0, you go to Euler, send the infinite number of layers. He put a very small noise on the smaller layer, then send to infinity. The noise disappears, like in convex integration, the R disappears. Remains a solution, unfortunately, let me repeat, in the words of Malibayev, remains solution not of Euler, but of some artificial model, and this solution are random. And this is what he says is intrinsic stochasticity. So completely different from the Peano phenomena, much deeper than the intrinsic stochasticity of a Peano phenomena. So he builds intrinsically stochastic solution of a system with infinitely many scales, perturbed by noise at the lowest scale, which goes to infinity, precisely like in convex integrations. So the link with the idea of convex integration seems almost straightforward, but how to put in practice, nobody knows. He doesn't know. He's trying to do, but he doesn't know. The link with the theory of dissipation by noise that I presented is less clear, but is like to say, this noise produces effects which go upward, and so at every scale, this scale, there is randomness, not because it's random itself at that scale, because there is a randomness coming from somewhere. So there is a randomness at this level, and this randomness acts on the upper scales in a deterministic way, producing also a decay of energy. So there is a flow. So I think that the theories of dissipation by noise are around here. Convex integration and intrinsic stochasticity are a little bit in the limit of this procedure. At the end, for the idealized models that he constructs, these intrinsically stochastic solutions are not like the Peano phenomena, namely you have a non-uniqueness, and this non-uniqueness is made probabilistic because you say this is chosen with probability 1 alpha and this with probability 1. No. It's really a Markov process. In time, continuously, there is branching continuously. At every time, it restarts in a random way. So this stochasticity, which disappears in his model, at the end, his model is deterministic. It's deterministic, but the solutions are stochastic Markov processes, which with ramification at every instant of time, exactly like in the solutions of stochastic differential equations. And his interpretation of his models is this one of Landau Lifshitz and of the thermal noise, which I don't know if it is correct or not, but sounds very nice in comparison with convex integration. Thank you very much. It's the end.
Thank the speaker for this exciting presentation. Certainly there are curiosities or questions for him. No question? To Mario.
Rescaling of different layers is the usual parabolic rescaling. I mean the ratio between the rescaling of time and of space.
In this picture?
In this picture,
I
yes.
choose the Kolmogorov theory, K41. This is K41 theory. Oops, let me use another. This one. K41 prescribes that the velocity moves like the length at power 1/3, and velocity is space over time, and space is L. So this is L over time. And so if you compute the time in K4 is length to the 2/3. So I choose the Kolmogorov scaling and computed the time scale of Kolmogorov scaling, which in turbulence sometimes is true, roughly speaking, approximately.
Any other question? If not, we thank again the
Thank
speaker.
you very much. Thank you.
Thanks. So we resume this morning session. I introduce the next speaker, which is Nicola de Nitti. Please go on.
Thank you very much. It's a pleasure to be here. So today we'll talk about some recent developments in local conservation laws, both from the point of view of regularity and long-term behavior. And these are several joint works over the past few years with a lot of collaborators, some of whom were also here this week. First, let me convince you, since this is the first food conference, of the usefulness of these non-local models. Well, let us take, for example, alpha Euler. It's a very popular model. It's a scheme introduced in the framework of large eddy simulations. Essentially, you take Euler and then you apply a filter to the velocity in order to cut small scales. And this is what you have in this case. In the case of alpha Euler, the filter is essentially the Helmholtz kernel. And then, here I'm writing it only for the 2D torus, but of course we can also write it in 3D or in a bounded domain. And this kind of model has attracted a lot of attention from the point of view of regularity results, well-posedness, of suitable solutions, and, crucially, whether or not this is actually a regularization of Euler, in the sense whether or not, as alpha goes to 0, we get the 2D incompressible Euler equations. And the answer is generally yes, under suitable assumptions. And here, this is just a small sampling of the papers in this area that cover both the periodic case, the case in a bounded domain, and so on. In particular, let me emphasize the last one, because this is of just maybe 2 weeks ago, and it shows the convergence using essentially techniques that come from the theory of regular Lagrangian flows. But now, I will not consider this non-local model. Rather, in this talk, I would like to study non-local models in 1D arising in traffic flow. Let us consider, for example, the typical LWR traffic model, just a scalar conservation law. But in the velocity function, instead of writing 1 minus rho as the velocity, so monotonically decreasing and so on and so forth, I write rather W of rho, where W is a suitable averaging of our density with some kernel gamma that acts as a weight for the average. In particular, notice that here I'm integrating from x to x plus alpha. If you imagine this at a microscopic level, it means that you have one car here, the one in red, which sees a few cars ahead, and then can regulate its velocity accordingly, depending on the density of traffic ahead. So this alpha here is just a finite number. At the macroscopic level, this means, of course, that you have some kind of averaging of the density going on. And now you can imagine that if one car can see ahead, then probably it will adjust its velocity in order to avoid traffic jams and accidents and so on and so forth, which is somehow what I want to illustrate in this picture here. You know, every car has a kind of a look-ahead radius and can adjust to avoid collisions. This is heuristics, but in fact, it can be proven. that there is a sharp difference between local and non-local conservation laws. For the sake of concreteness, let me fix going forward the velocity Lipschitz continuous, maybe W1 infinity lock, and monotonically non-increasing, as it's consistent with traffic modeling. So this is the local conservation law. Imagine V1 minus rho being the one of LWR. This is the non-local one. For the local one, famously solutions break down in finite time, the gradients may blow up and so on. For the non-local one instead, the solutions actually preserve the same irregularity as the initial datum, roughly speaking. Also, you don't need to impose entropy conditions in order to select a unique solution. In fact, by some kind of fixed point argument using Banach fixed point theorem, you can obtain a unique weak solution just by using somehow cleverly the method of characteristics. These are some of the fundamental differences. Then, of course, it all depends on which weight gamma you select, but these are the most fundamental differences. Crucially, let me also emphasize that the non-locality makes the speed of propagation of information infinite, but the mass still propagates with finite speed. So the model is somehow hyperbolic, let's say. These are a lot of claims. I'm not going to prove any of them right now, and this is just a short bibliography where you can find more details if you want. But these by now are more or less classical. Let me emphasize, for the sake of advertisement, the last paper here, which is a bit more recent, in which we prove these claims for gamma being only BV, as opposed to more typical assumptions that are gamma Lipschitz as well, or even more. So I will not prove any of them, though. Let me just focus on these characteristics that we've been mentioning, because maybe they can a little bit stimulate your fantasy. What do I mean by characteristics? If I assume that W is fixed, just space and time dependent, Lipschitz, then we only have a linear transport equation with a Lipschitz velocity. So I don't even have to go into all the theory that we developed in these days, but I just write down the solution with the classic method of characteristics. But then I remember what W was. W was the convolution of rho with gamma. So I plug in this solution formula into W, and I end up with a fixed point problem, with an integral equation, a fixed point problem, that in fact can be solved by Banach fixed point theorem. You have to work a little bit, but in the end it works out. So the behavior for this kind of local conservation law is very nice comparatively to the local problem. The question remains, though, is it consistent with the local model? That is, if you let alpha go to 0, that is, the averaging kernel goes to a Dirac delta, is it true that the solution goes to the one of the local conservation law? And this, of course, is of interest by itself, mathematically, as a question, but it's also important from the point of view of modeling, because you would have to have some consistency between the non-local and the local modeling for traffic, for instance. And just for the sake of completeness, let me recall what I mean by the solution of the conservation law. I mean entropy solutions, of course, in the sense that for every convex entropy eta and corresponding entropy flux Q, defined like this, the solution of the local conservation law should satisfy this entropy inequality here in the sense of distributions. So this is, I'm focusing only in the case when we have entropy solutions for the local conservation law. This question has attracted a lot of interest in recent years. Let me just give you very quickly a short survey of what went on. So the question actually was studied first in 1999 for a regularization of burgers, but under the very special assumption that the limit profile for burgers is smooth, which of course we know generically is not really the case. In a similar spirit, much more recently, it was studied for the case of monotone initial data, but also that is in the same spirit in the sense that if the initial datum is monotone in the right way, then the solution does not have shocks, only rarefactions. So this also helps for the sake of the convergence. More generally, in this numerical paper, Amorim, Leonardo Colombo, et Teixeira emphasized that the convergence should be expected, but again, numerically. But in fact, after that, most of the results have been negative. So in particular, 2019, a breaking point, Maria Colombo, Gioca Kripp, and Laura Spinolo showed that in general, there is no convergence to the entropy solution of the conservation law, with some kind of pathological kernels, but still there is no convergence. In general, even more, a few months later, they show that there are no uniform total variation bounds on the alpha approximate solution, which of course in principle means nothing because you can get compactness otherwise, but still it's an hindering to get to the convergence. On the other hand, if the initial datum is nice enough, in this case nice enough means bounded away from 0 and one-sided Lipschitz, then the total variation bound does hold, and then you get the convergence to the NTV solution and so on. Relaxing the assumption the initial datum is then crucial, and this came a bit at the expense of the kernel a bit later. Exponential kernel, initial datum only in BV, so not one-sided Lipschitz, but still bounded away from 0. This is an important paper by Alberto Bressan. And then, of course, in all of these situations, if you add viscosity, that helps a lot because it brings us a bit in the situation of the first two papers. We have to calibrate the way in which viscosity and non-locality go to 0, but the viscosity helps. In this talk, starting from this summary, I want to present 3 more recent developments of the last 1-2 years. The first is the development in the case of an exponential weight in the non-local conservation law, but initial datum general in BV. The second development is in the case of convex weights and initial datum only in BV. And the third and most recent is the case of initial data only in infinity and the Loneric type regularization effect, hence the title of the talk for the local conservation law. Let me start by the exponential setting. The setting is this. The non-local conservation law that I wrote in the first slide. Here the kernel is exponential. I'm integrating between x and infinity, notice here, instead of from x to x plus alpha. This is for technical reasons, of course, because integrate from x to x plus alpha, let me anticipate, is an open problem for the sake of convergence. But it's not too bad, because still the exponential kernel, of course, decays at infinity very fast. So from the modellistic point of view, somehow it's not too terrible to have a further domain of integration. Why the exponential kernel? Because it's very nice, of course, because it grants us additional structure. In particular, the W, so defined, satisfies this ordinary differential equation. And this will play a fundamental role. So the question, to summarize, is we want to say, when alpha goes to 0, what happens to this rho alpha? If it gains a bit of regularity, if it propagates a bit of regularity, this evolution, and ultimately whether or not this rho alpha converges to rho. As anticipated, the answer is yes. So for the initial datum, L infinity and bounded variation, not necessarily L1, maybe only L1 lock. We assume the velocity to be concave, or for the sake of traffic modeling, but I could say similar things, changing a little bit the integration for convex fluxes. Then, under these assumptions, the result is rho alpha is bounded uniformly in infinity. It satisfies also a uniform BV bound, and it converges rho alpha and also the W alpha, both converge, in fact, in L1 lock to the solution of the local conservation law. They both converge, the whole family converges. I'm not here extracting subsequences, but this is somehow a standard remark because of the uniqueness of entropy solutions to the conservation law and the Eurasian criterion for subsequences convergence. What is the key idea in none of this business? The examples from before showed us that there is not much hope to gain regularity or compactness for rho alpha itself, because BV bounds for that don't really hold unless the initial datum is more particularly chosen. On the other hand, W alpha is much nicer because it's the integrated version of rho alpha. So this helps a lot morally and also practically, because in fact, using the ODE structure here granted by the non-local kernel, we can write an evolution equation satisfied by W. This is just a simple computation, plugging in computing the derivative of W and plugging in the PDE. A simple computation to do formally, to do rigorously also simple, but it takes a little bit of care to argue with the characteristics. But this is a fundamental point, because then this equation, this is a conservation law. Here I'm writing it in advective form, though, with a non-local source. Non-local source that doesn't look so good to just look at it like this. but in fact, it behaves well enough in the sense that with a little bit of patience, one can prove VV bounds for W alpha. And this, of course, gives us the required compactness for the convergence, and also tells us the information that the VV regularity is not preserved for the density, but is rather preserved for the average density. Similar idea applies to more general kernels, and this was the more recent development that I mentioned in the second bullet point in my table of contents. More general kernels, crucially, satisfy these assumptions. Crucially, they have to be convex. So this prevents us from having it piecewise constant, like integrating up to alpha and then dropping to 0. But still, under these assumptions, it is possible to write an evolution equation kind of similar to the one above, and to get then BV estimates for this as well. In addition, if you also assume this integrability on the kernel, which is satisfied, of course, for the exponential, you also get the convergence with a rate for W, though, not for rho alpha. With a rate that, notice here, matches the one of Kuznetsov for the viscous approximation, except that here there is an alpha, because, of course, here the initial datum W alpha 0 is also averaged, so this is expected somehow. It's perfectly matching the classical viscous theory. Let me just, in a few words, summarize the key steps that I've been hinting at so far. So existence of uniqueness without entropy for the local problem, done. The methodological characteristics that I mentioned before. The uniform and infinity bound. This is where we have to be very careful to pick the monotonicity of the velocity and the integration, if it is from x to infinity or from minus infinity to x, carefully. But if the two match, then a formal computation here shows us that, in fact, the point of maximum should decrease for the non-local solution, and this computation can be made rigorous also, of course. The third point is to show that actually W alpha satisfies that non-local equation, which again can be done rigorously. And then after that, the BB bound. Here, this is, of course, the most involved step, but I'm not showing the computations for today. But once we have the BB bound, then we use classical compactness theorems by Ellie to get then the compactness of W alpha, the familiar W alpha in L1 lock. And then we have to show the convergence to the entropy solution of the conservation law. This is also requires a lot of care to be done, but I'm not showing you the computation, but you can believe more or less that the non-local source in the equation for W behaves well when trying to see how it dissipates the entropy. Let me illustrate these points with some pictures. The first line is exponential weight, exactly our setting, exponential weight, initial datum that is this piecewise constant. The three pictures are smaller and smaller values of alpha. The solution of the conservation law, the local conservation law with this initial datum can be computed explicitly. And if alpha is chosen and small enough, numerically we see the convergence. The second line instead is a line of hope, because that is this is a simulation for that piecewise constant kernel that I was mentioning, this one over here. For this, the current results don't apply, but the simulation kind of suggests that maybe they should, or maybe we should take a look at them more carefully to see what goes wrong or goes right. A second numerical simulation to illustrate the fact about the total variation. So for rho, it may increase. For W instead, it decreases. Again, for a very particular initial datum. The first line is for the exponential kernel. The second line is for the piecewise constant kernel. The second line is kind of deceiving. It's too optimistic as a numerical simulation, because with this initial datum, it is open whether or not the total variation decreases for the piecewise constant kernel. But it has been constructed a very particular initial datum, very pathological, that is in BV, but for which the evolution makes the total variation increase, not blow up, but increase. So this second line is of hope, but is a bit too hopeful in a sense. But still, the problem remains. Let me now switch to the second half that I was promising. the regularization from L infinity to BV. This is, of course, a classical result by Olenek in the local setting. In the non-local one, it takes stronger assumptions. In the local setting, the typical assumption for the Olenek regularization result is strictly convex flux or strictly concave flux. In the non-local setting, it takes a bit more. You see here, I have technically looking hypotheses that are a bit stronger than just, in our case for traffic, strict concavity. But still, under these assumptions, we can obtain the classical Olenek inequality. Again, here the flux is concave, so don't be scared by the sign there. And the strategy is once again to write the equation in W and to then compute the derivative and show appropriately an Olenek estimate. I will not go into these details, but let me point out that the derivative of W in X has this term here in the non-local source. And this inspires us to say, is it true that this piece here, this one in red, satisfies itself some kind of bound? And the answer is yes, it does. Again, under strong hypothesis, but this term here has a one-sided bound. And with this in place, we can show a total variation bound, very classically, and then a convergence result. Again, convergence regression result for the initial data in L infinity. And these are, once again, some numerical simulations showing you the decay as we expected it, or as we expected it from the theorem. Once again, the first line is the theorem. The second line is the hope for the piecewise constant kernel. With all of this done, let me conclude this talk with a short remark about the long-time behavior. For studying the long-time behavior for local conservation laws, the Olenek inequality plays a fundamental role. For us, we do have an Olenek inequality in the local case, but in fact, among all those hypotheses that I skipped over before, we have that the very clean hypothesis is for quadratic fluxes. So let me now turn to non-local burgers, like this. And here the problem is time to infinity. Now, you will ask, what does it have to do with Olenek or with the regularization that I was mentioning before? Well, the relationship comes from this rescaling. This is a classical approach that you also use in the local case. You rescale the density like this, and you end up with these rescaled burgers. And then, of course, you notice that letting lambda go to infinity is the same as letting time go to infinity. So this and this, when lambda goes to infinity, the rescaled problem here behaves exactly as in the localization limit. The difference, though, is that in our case, the initial datum is not bounded in an infinity uniformly because it goes to the Dirac delta. And this is what requires the Olenek regularization effect. The result, as in the local case, is that the long-term profile is the n-wave solution for the Burger's equation, the fundamental solution having the Dirac as initial datum, which is an explicit profile like this. Notice here that in all of this business, I'm having initial datum bounded being positive. So this is half of the n-wave in the more classical sense of the word. The key steps of the proof, then, are all based on the Olenek inequality, that once again here looks very nice. And then the rest of the strategy is what you would expect. From Olenek, we get an infinity total variation bounds for positive times. And out of this, compactness away from time zero and lock. And then many technical complications arise when you want to have the convergence up to time zero, so getting the Dirac as the initial datum, and in an infinity, not lock, in order to have that the final profile is the n-wave with the exact the mass that you would expect from the initial datum. Once again, let me show you some pictures. These are convergence to the n-wave profile for several initial data in our setting. You see, either we start with a characteristic function, or already with something that looks like an n-wave, or with a more regular initial datum, or with some superpositions of characteristic function and wave, but in all cases, the numerics show us the theorem that we obtained. The second slide is once again one of hope, because here we have various initial data, and on the one hand, in the first line, piecewise constant kernel. Second line, more general fluxes, cubic instead of quadratic, where the result is not proven, but the numerics kind of suggest that it should be. This is the relevance that I wanted to show you. Let me just conclude with some problems for the future. Of course, I already mentioned many in the numerical simulations, but let me emphasize once again that a crucial problem is the case of piecewise constant weights with integration here from x to x plus alpha, constant kernel here, which of course means that then the derivative of w is this. And you already can imagine from looking at this that proving BV bounds will be very difficult for w, because then this reflects in a translation estimate on rho, roughly. And in fact, there are these counterexamples that I mentioned where very particular initial data lead to increase in the total variation. But then the problem of the compactness and of the convergence remains open. Final problem that I want to mention is the boundary value problem, which I didn't mention at all so far, but this of course is very relevant for traffic. The boundary datum is put on both sides of the boundary. On the one hand, as an influx datum. On the other hand, it is in the non-locality, where the integral is up to infinity. So we have to put here some input for this integral from the end of the domain up to infinity. This is a good model in the sense that it is well posed. There are several regularity results available. There are several control results available in this recent paper where we control from both sides of the boundary, modeling, control given by traffic lights or things like that. But for the sake of the convergence, this is open. So with this problems review, thanks again for the invitation, and these are the references that I took the results from. Thanks again.
We have time for questions or remarks, if any.
Is anything known for systems?
In a sense, there is a recent paper about systems, but with a very weak coupling, in the sense that the coupling is not in the flux, is in the sources. And the sources are bounded and they're Lipschitz. So in that case, you can recycle essentially all that we've done so far, and then the source is just very nicely behaved. For systems with a more suitable coupling, let's say, in the flux, then it's easy to do for not easy, but it is easier to do for triangular systems in which the first equation is one of these that we covered in this talk. And the second equation is linear in the flux with respect to the other variable. In that case, for the first equation, you use what you have done now. For the second equation, you use classical stability results of the type of Bouchot-James for linear transport with one-sided Lipschitz fluxes, one-sided Lipschitz velocities, and then you conclude. But for really, really strongly coupled systems, it is completely open. So in case you want to get into that, that is also a very promising problem.
Thanks.
I should, of course, mention alpha Euler, but that is somewhat a different situation as a system. So.
Any more questions? If not, we thank again the speaker. The speaker of this morning session is Stefano Bianchini from the CISA of Trieste.
Okay.
Please go on.
So it's so I want to talk to a strange problem. At the end there will be an ODE, but strange ODE, okay. So the why I got interested into this problem is because Martina Zissa, my student, was tired of doing the subject I gave her. So I asked if she wanted to change, and I said, "You want to have a look to this one?" She said yes. And then it turns out the problem to be very complicated, for me. So let me start what is the blocking fire problem. So blocking fire problem, in the simplest way, is that you start with the fire in an open region, omega 0, and the fire evolves in every direction with the speed, which is fixed equal to 1. So it's the homogeneous problem. And you can construct barriers And barriers are, well, at the end there will be rectifiable sets, actually even better. But okay, at the end, let's say at the beginning they're just Borel sets. And so the fire has to evolve avoiding the barrier. So for example, here, to arrive to this point, the time it takes is the minimal curve, the length of the curve with minimal length connecting one of this point to the region. Okay? So, and what you observe is that, well, the barrier can be, you can interpret the problem into two ways. The first is that you are building the barrier at any time, and then the fire and an interval of time increases, and in that interval of time you build the barrier, and or you give me the barrier, and then I solve the Hamilton-Jacobi equation, the iconal equation with barriers, which is the same. So if you interpret the problem as you give me a configuration of barriers and you want to solve the Hamilton-Jacobi, the iconal equation, then okay, you have two different parts. So you have a part of barrier where the fire has not yet arrived, and the part which is already burned. So the difference is that, in some sense, well, you can think that this part I can change it. No, it's not required to be exactly as in the drawing. While I'm here, well, if I change the barrier, I change the fire, and if I change the level set of the fire, the burn region is the level set of the iconal equation, and so if I change the level set, then it may be this part which was not touched by fire is going to be touched by fire. For example, if this is magic, so if I, by chance, stupidly, I make a hole here, then the fire arrives at time t already here, while if there are no holes, clearly it has to go around and it never touches. So in some sense, the future of the barrier is chosen by what you do in the past. Okay, indeed, this is the problem. Okay, so let me state now, formally, the way I interpret is not as a control problem when you choose the barrier time by time, but you give me the barrier and then I solve the iconal equation. So you give me a Borel set with finite length, and okay, a priori the final length turns out because you want to have let's see, the function you want to minimize. So the fire is what is propagating in every direction, starting for an open region, omega 0, and but it cannot cross the barrier, which means that essentially, well, you solve the iconal equation, and then well, the level set at time t is what is all the points which can be connected to 0 to the initial burn region with a curve of length less than t avoiding the barrier, as in the drawing. Okay. So and now let's start with, so if I can build a barrier, well, the barrier that I want, clearly there is no problem. You should just take the boundary of the set, of the initial set. However, you have some cost, and typically the cost is how much, so there are constraint and cost. So the constraint is that you cannot build the barrier with infinite speed. So if I discover a fire, clearly I cannot imagine that in time t0 plus, I have already 2 kilometer barriers. So that's a problem. And this is expressed into this constraint. So let's set that psi sigma is the speed with which I can build the barrier. So the length of the burned region at time t, and here I come back with my interpretation that if I fix at time t, I have to decide what to do next. So this tells you that the length you can build next is such that you cannot have more than sigma time t already built. So essentially at time t, you cannot build more than sigma t. So this is the speed with which you can build the barrier. And there are other functions. Okay, so this is the constraint, and at this point you can say other function. For example, I want to minimize the area plus the length of, or just the length, or whatever. But here we are interested into the existence of at least, so the minimizing problem, you have to start with something which is not infinite. And so the existence is that you have at least one admissible barrier which blocks the fire. So, and I think, so the fire blocking problem is that if there exists an admissible barrier, so you know that the burned region is less than sigma t at time t, and the fire is blocking finite time. If I solve the aconal equation, I have a bounded region when it's finite and outside is infinite, the solution of the aconal equation, meaning that the fire never goes outside that region. Okay, so this is the setting of the problem. And once you know that you have an admissible solution, then you can ask the optimization. So I want to minimize some convex cost of the area, and or you have a functional or an integral of the length, whatever. You can put several functionals, the convex, lower, semi-continuous. The real thing I'm interested is if there exists an admissible solution. Okay, so let's see some examples, because the feeling is that you have two main ways, two main optimal ways, but this has not been proved, to build barriers. So the first one is that essentially you have two people that build a barrier at the same time. So if you do the computation, this is admissible. Well, two people means that the fire burns 2 points at the same time. And now you check what means to be admissible. It requires that the speed is larger than 2. And here, okay, if you take this angle here, you say what is the speed of a building. I mean, if this increases by 1, this increases by 1 over cos alpha, the same over here. So the speed is 2 over cos alpha, and alpha is the angle. Very well. If sigma is greater than 2, I can choose certainly an angle. And okay, this heart-like region can be as large as you want when alpha is very close to 0, but in any case, it's okay. Sooner or later, you're going to close the fire and circle the fire into this heart-like region. So this was proved to be optimal within the simple curves. If sigma is larger than 2, optimal with respect to, okay, here I have to say something. So this part here, the shape depends on the functional you want to minimize. And, but okay, for the rest, so this is the non-saturated part. So it's the part where you build the barrier, but the fire is not already there. This part, the green part, is that I'm building the barrier, but the fire is next to me. So I cannot choose what to do. I'm forced to do with some particular speed. And, okay, so, well, also, there are results that once you know that there is a barrier, I can change the cost. For example, I put the cost will depend on the point, and I can say that depending on the point, I have different speed in building the barrier, and then, okay, there are optimal strategies. There existing optimal strategies, but the key point is that if you have at least one, and one admissible does not depend on the cost. Okay, so here for sigma greater than 2, there exists at least one, and we are happy. But one can invent another strategy, which is suggested by Bressan, and instead of having 2 people, I have only one guy that started digging a barrier somewhere, and it tries to encircle the fire, so at some point you can close it simply because the fire has to take a long time to arrive to that point. And since you are faster than the fire, maybe you can close it. Okay, so, so Alberto Bressan did some computation and sort of, well, he proved, not completely analytically, but the proof clearly can be made formal, that you can do that if sigma is larger than 261, which in some sense is reasonable. If I have 2 people, I can go slower than if I'm alone. I have to run faster. So the formal analysis is done by this guy here. That basically they are able to rewrite this picture finally into some ODE. And then this ODE is a retarded ODE, but still it becomes an operator, and the operator you can study, and you prove that if sigma is larger than 261, okay, then all the eigenvalues are complex, and if the eigenvalues are complex, the solution oscillates, and the first zero means that you arrive there. Okay, let's see now how to formalize it. Okay, so before I want to see why, so now the thing is if sigma less or equal than 2, you can prove that is a closed set. That's because the starting region is open. Then the fire cannot be blocked. So this is the conjecture. And let me see, I want to show you that so for sigma less or equal than 1, it's quite easy to prove simply because the fire is faster than you. There is no way you can block something, catch something which is faster than you. And for example, I want to show how a simple way of proving that you cannot use a simple curve if the speed is less than 2. And the basic trick is that you deform the region. So let me give a simple curve, the black one, and then you start deforming it and proving that every deformation if the back is admissible, also taking the convexified is admissible, simply because it takes the length you gain by removing this this black part. Remember that the admissibility functional is the time, sigma time, minus the length. You can prove that if sigma less than 2, then the length you gain is larger than the time. So at the end, this decreases. This increases. So you have more space. And then once you arrive to the purple one, if sigma less than 2, you discover that, well, if I shrink it to the region, it's even better. And finally, okay, at this point when you are in this green part, well, it's just a computation. It's impossible simply because the time is this length and the boundary is greater or equal than 2 times that length, actually strictly greater. Okay, so contradiction. So what suggests this approach is that, yes, you can start with very complex Borel barriers, but at the end you simplify into a situation and then you do the computation. Okay, so the other is what happened, and well, this is I invented. I'm not able, let me say that so far, I'm not able to treat the general barrier and to simplify it. So what we decided is to take some structure and see what we can compute, hoping at some point to come up with a general approach. So what at the end, what I cooked is in between the conjecture is that let's show that if I have a spiral-like structure, so I'm just alone, I want to run around the fire until I'm able to block, then I get the critical exponent. So what was proved by these guys is that if you have the golden ratio, the speed is less than the golden ratio, you cannot. The proof is clever. In some sense, they assume that at this point, the fire has already moved by a length 1 along the segment. And then, okay, you do the computation, and then you prove that with this speed, it's written here, but you can forget, when I build this segment, the fire has already moved by length 1 over here. So essentially, you can never close the fire simply because if you arrive at some angle pi, as angle phi minus pi half is such that the fire is already out of the barrier. Okay, so the computation is just these 2 lines. It's not complicated. There is one problem here. You cannot, well, you can refine slightly the computation, but clearly you cannot reach the critical exponent simply because they don't say anything about the structure between these 2 points. It can be a segment, but my requirement is that I'm just building the fire alone. So it can happen that in some point the level set of the fire is burning 2 points at the same time. This is not admissible. I mean, I'm coming back in the situation here where I allow the fire to burn 2 points at the same time. Okay, so Very well. So at this point, essentially, we know that for sigma less or equal than 1 is impossible. For the spiral, sigma less than 1 plus square root of phi is impossible. So I want now, my goal is to suggest the proof we have to reach. Okay, now it's we can reach 2.4. My feeling is that I'm not smart enough to guess how to arrive to 361. The method is working and is completely general. And at some point we have to choose the guess, and I'm not smart enough to choose the guess. So I can reach 2.4. But it's changing. I mean, before so I thought it was okay up to the conjecture. Then I discovered there was a term, so 2.4, it's okay. So let's start with the how to do. So far, the thing up to this computation is that is just some drawings and very simple comparison. So now we have to dig into the more complicated into the model, how to modelize. So first, some simplification that you can forget. Essentially, you can say that I can assume that the fire starts in the origin and the barrier is outside the unipole. We can forget. This is just for let's say. So this assumption is just to the problem is scaling invariant, and I put a scale. That's it. Okay, so the important thing is the region where I can choose the barrier. So I have to define the functional. So the admissibility functional is that at any point x, given the barrier, I measure the time it arrives to x minus the length divided by sigma. So this tells you that at time t, I never build a barrier which is has length more than sigma t. And so to be admissible, a barrier means that if I compute these two quantities, I mean, which are defined, given a barrier they are defined, I have to check that this thing is always positive for any point of the barrier. Okay? So, and now it turns out the two parts that I already suggested. So one is the saturated sets, and this is when the points that are basically on the barrier of the admissibility region, on the boundary of the admissibility region. Here, when I'm here on the boundary, I have to be careful. I cannot do whatever I want, because if I choose to build a barrier, I mean, too fast, then I'm outside the admissibility region. While when I'm inside this, let's say, open set, clearly I can deform the barrier as much as I want. So here, basically, the barrier cannot be deformed. But while here, you can choose the best that you want. Okay, so with these two things over here, okay, and now the problem is, well, now I have to choose the functional. I want to have a barrier with finite length, so one admissible, and I choose my optimality problem is the one that blocks the fire with minimal length. So it's clearly these are the admissible ones. Very well. Okay, so now we start with just to have a feeling on the problem, a very simple thing. Instead of having a closed curve, you have a closed curve with an interior segment. And now the computations are already complicated. So basically, you prove that the outer part apart this point is convex. Then you have to do some other computation to show that essentially you have a segment here, and you have some final segments. And okay, other simplification. At the end, you obtain that the optimal one, the one with minimum length, has the following form. You have a segment, and this one is saturated. And actually, the last point, so this length is the last point that the fire arrives. Okay, so now the configuration is sufficiently easy. You can do the computation now, and you do by some geometry computations. You get that, unfortunately, after you arrive to pi half, this configuration cannot be admissible. So essentially, you can block the fire just for an angle pi. Sorry, pi half pi. Okay. Okay, so now we come back to some more complicated, which was the spiral. Let's try with the spiral and prove that the critical speed is 2.61. Very well. So we have now to define what is the spiral. The spiral is not a spiral in the sense of you have a point and then you have the polar coordinates, but it's the spiral from the point of view of the fire. And the point of view of the fire is that if the fire is here, it sees only one point in the barrier. The green part has already been burned. And okay, then I have to decide the shape. Let me say that for the optimal thing, some of these assumptions are redundant, but let me say that I start with the direction which is counterclockwise. It's convex, and at any point, I mean, the instantaneous burning of the barrier is a connected arc. So I'm never burning. Essentially, you can say it's one point, but when I do the limit, I get a connected arc. So I never burn it more than 1 point. So that's the definition. And then with these assumptions, I have a description from the point of view of fire, which is the following. When the fire arrives here, it sees this length, and this length, so the fire has turned an angle phi, and then it sees this length, which says that this is the opening that the fire sees. So when I'm here, so the fire sees the door open for spreading, exactly equal to this R. And so I can describe the barrier in terms of phi and R phi. So I give you the rotation number phi, so how many turns the fire is going around the origin, and then the door, I mean the gap that the fire sees in the barrier. So clearly when R phi becomes 0 is exactly when I close the fire. Okay. Oh, so fantastically, with this description, I get an ODE. So, and you compute, and you obtain that if my control parameter is the angle between the tangent of the spiral and R, so I get that this is the equation for the R, and that this phi prime is the angle here. Sorry, I forgot this is, sorry, yeah. Yep. So this was the angle phi prime. This is the radius of curvature in this point. Well, it's just a geometric equation. So the thing is that now I can start looking at this ODE. This is a delayed ODE, delayed differential equation, and the delay depends on my choice of beta there. So it's a delayed equation where the delay depends on the control. It's a delayed control equation, and the delay depends on the control. I don't know how to analyze it. So, okay. So more or less, now I have something formal, and the requirement clearly is that the admissibility functional is positive, and I can, in this coordinate, write it. So is I start with 1, then it goes around up to the length to this angle phi prime, and then it takes this length to arrive there. So this is the time the fire takes to arrive to this point, minus 1 over sigma I represent since it's less than, so I write in this way, sigma is between 1 and 2. Actually 1 and 261, so I write into this way. And this is the length of the barrier to arrive to that point. So I have to solve, I mean, I can choose any beta such that this holds for any phi, and I hope, I'm asking if I can, there is a choice which makes r, small r of phi equal to 0. So now now it's quite formalized. Okay, so so my problem, let me say, is that it's a little bit strange here to say the one that closes with minimal length, because I'm working on an empty set. Something which is not empty certainly is the following. So you fix an angle. For example, fix this angle phi bar. And I want to choose my parameter beta in order that this length here, so the R of phi bar, is minimal. That's now the set is not empty. So the minimum exists, and I can hope to prove properties of this minimum. So essentially, instead, I'm asking, fix this angle, this rotation angle, which is the choice of the parameter beta in order to be admissible, in order that this opening is as small as I can. Clearly, in the moment I get something which is less or equal than 0, it means that at previous time I blocked the fire. So, and now we start with some examples, which were not known, at least it was not known to me. So, for example, let's choose a barrier where the speed is equal exactly to alpha. Sorry, the angle, this angle here, beta, is I choose equal to fixed. Beta equal to some alpha fixed. Exactly actually the angle over here. So if I do the computation, it says that this is certainly true. It's automatically true. Okay, so here I get now retarded ODE, but now the interval is not depending on the solution itself or my choice. So I specify what is the initial data. You can prove that the correct initial data for the barrier is this one, and now you can solve it. And well, first we plug into, well, it's linear, so it's an operator. It's a compact operator, actually. You can rewrite it as a compact operator, but the spectrum of the compact operator is complicated. And the problem is that I'm starting with a specific data. I want to prove that with this data, either it closes or it blows up. So I didn't know what to do. At the end, we come up with an analytic proof. At the beginning, we just plug into the computer, let's see what it does. And you obtain this 261, more or less. So the computer says that below 261, it's blowing up. Above, you close it. Then now there is a proof. But okay, so this is just a specific barrier. Is not really the optimal one. So now how to do, okay, and this is indeed so how to prove essentially analytically, well, at least gives the hint why this is the correct constant, is because if this is a linear retarded ODE, delayed retarded ODE, so what you do is just say, look for exponential solutions, and it gets you an eigenvalue equation, and you see that it has real eigenvalues only if this holds, well, above this thing, below this thing, you don't have real eigenvalues. So that's more or less the analysis. But the thing is that this is a specific barrier, is not the general one. So now we have to prove what is the, either give a hint or to prove the thing, that it doesn't close, or give a hint how it closes. Okay. So now I'm basically at the end of the talk. So the fundamental idea is the following. So can we build a model of the optimal barrier? And the answer is up to an angle even slightly larger than 2 pi. Yes, I have an explicit choice of my control parameter beta, which gives me the optimal one. And basically the idea, so this is the example when it starts. So you start with a level set of the fire, and then a segment, and these I know from optimality conditions that they are the only allowed structure in the non-saturated part. When it is saturated, I start with the spiral, so the previous ODE, and so all the parameters are perfectly computed, and you can prove this is the optimal one. So we were so happy because we thought, probably, well, we were not childishly, that if you proceed with the saturated spiral should be optimal. Okay? And it turns out it is not. Indeed, what happened is the following, and this is the problem of the retarded ODE, that if you do a perturbation, then it takes maybe several cycles until you see what is going on, no? And indeed, here is an example. So if I perturb a little bit the barrier, like here, okay, since I know that up to this angle it is optimal, certainly the green one, the perturbed one, it stays outside, out exactly of one angle, which depends on the perturbation. At some point, it crosses, it goes inside. So I'm in trouble now, simply because not only we prove that, well, it cannot be optimal, but still you can hope to be optimal. But actually, if I change, so this is not optimal, for example, the black one, if I take, okay, let me think. Let's take this angle here, okay. So let's say I fix this angle phi bar, and I want to ask what is the barrier such that this gap, this gate for phi is as small as I can. Well, there exists an optimal barrier. But if I change the angle, for example, I ask the angle here, the barrier is different. So you see, I'm really in trouble because we were in trouble because we don't know how to, I mean, there is no an optimal barrier that is good for all phi bar, but for the initial rotation. For initial rotation, yes. After, it depends on what you do at the previous step. And well, it was almost impossible for us. In fact, I'd have to say that many of these things came out by simulations. So we just plug into the computer and see what was going on. And finally, we reproved the stuff. But at the beginning, I didn't have a feeling of what's going on. I mean, it's just... So to conclude the thing, I give you a sketch or how to arrive to 2.4, basically. So I do not need to have really an admissible barrier. So what I need is a family of solutions, which are the black one, which stays inside all the admissible barriers. So the guess is how to build these solutions. And it turns out that one idea that works for sigma larger than 2, but not to the critical one, is that once you finish, here you subtract a positive part, which you can compute depending on, is a function of the barrier itself, but it's positive. And now, okay, so you have a family of spirals, which are built like, okay, you take the optimal one, and then at some angle, subtract the positive part, and the angle and the quantity you subtract depends on the spiral itself. But okay, in any case, it's explicit. And now you run the computation in the following sense. So you start with, you give me a barrier. From any point, I build, let's say, I use the same choice of angle I do here to build another barrier. So essentially, my control parameter from now on is the beta that I have chosen at the beginning. So there is a specific choice. And so I build a green curve, which has nothing to do with an admissible barrier. It's just, at the end is a family of curves which are almost solution to the retarded ODE. And the property of this thing is that you want, if I start with the same procedure from another point of admissible barrier, this thing stays out. So essentially, in some sense, the idea is that let me draw phi and r of phi for the admissible barrier. Well, here, I don't know if it's growing so, a priori, but what I want to say is that, okay, from any point I build almost a solution. There is some perturbation I must add, and this family is increasing. Very well. If the family is increasing, certainly the barrier, the orange one, is larger than my initial barrier, and my initial barrier I can compute to blow up. So it's not a barrier between cohorts. It's a pseudo barrier. It's not admissible. It's just a trick. So, so the general approach is the following. You build some sort of family of sub-solutions, and you prove that whenever a barrier is admissible, this family is increasing. The initial is blowing up, and then clearly your solution should blow up. So the trick reduces, let's find this family. And that's why we have 2.4, because what the choice we do, there are other choices that work for different parameters, but at the end, you never get to the end. So I choose to subtract the thing here. There is another possibility, the fact that I decide at some point to switch to a faster speed. So essentially always is what is the beta, the parameter beta, which controls the retarded ODE you choose. So far we are not smart enough to prove what is the good choice. So the technique works automatically. Once you have the choice, the problem is the choice. So, and this is basically the proof. So you have a guess which is almost the optimal one. And so essentially this is almost the optimal one, but with some perturbation. The initial one is exploding, the family is increasing, and okay, should be close to the optimal one, at least from 0 to 2 pi. And okay, and you do the computation and show that this family is an increasing family, so the best one is the one that you have at the beginning. So this is the end of the talk. The guess is that these two, the heart-like shape, so the heart-like shape and the spiral, they should be the two possibilities you can have. All the others are not optimal. But so far, it's completely open, and the thing is that you cannot touch an internal barrier. So if I have an internal barrier here, you cannot touch in a very simple way. We never get how to, the hope is to remove it, but actually is not possible. Certainly is not possible to remove in a naive way. The thing is, seems like, you see, if you have this function, which is the length of the barrier, maybe you have a local minimum, and to guess the best, the optimal minimum, you have to climb up, but it seems, I mean, to make a jump, so to compare two different barriers which are not deformation one each other, we have no idea. Okay, so this is yeah, thank you.
Are there questions or comments? No question. So we thank again the speaker. So welcome for the afternoon session. We resume, and next speaker is Laurel A from Princeton University, which is speaking about PDE problems in thin filament hydrodynamics. Please go.
All right, thank you. Thank you so much. Thanks for having me here. All right, so the title of this school is very, very broad, and so, the thing I'm going to talk about today is probably quite a bit different from a lot of the other things that we've been hearing about this week. So let me start off by sort of painting the picture of the sort of fluid regime that we're going to be thinking about during this talk. So here we are at very, very, very low Reynolds number. So here at the microscopic scale, so very, very, very viscous environment. And sort of the phenomena that we're interested in here is really the interaction of these very thin structures, so these sperm tails, for example, with the surrounding fluid environment. All right, and so that's kind of this is kind of the picture that I want you to keep in mind as we go along. This is really the regime that we're interested in. And so just as a flavor of the types of problems that I like to think about, so there's a lot of sort of computational modeling that's been done for phenomena at low Reynolds number. And so I like to think about some of these models from a PDE perspective. And so with the goal of sort of more precisely determining when are these models valid, and then hopefully giving us, some information to hopefully derive some novel models that are valid at low Reynolds number. And so I want to take these basic mathematical models used primarily in numerical simulations and justify them from a mathematical standpoint. So in this talk, I'll focus on two aspects of that. So starting from a static picture of just a filament at a snapshot in time in a low Reynolds number fluid, and then touch on dynamics later on. All right, so let's start with the static picture, which I summarize as really the mathematical foundations of slender body theory. And so, okay, what is slender body theory? So, okay, so let's start by considering a closed filament, very thin filament, with constant radius epsilon. All right, so just for simplicity, it'll be a closed filament. We can consider free ends later, but for now, closed filament, constant radius. And it's going to be, so it has some thickness and it's immersed in a three-dimensional, very viscous fluid, so which we approximate by the Stokes equations. All right, so outside of the filament, the fluid satisfies the Stokes equations. And then if we wanted to most accurately capture the interaction of this filament with the surrounding Stokes fluid, then of course we would want to be prescribing some boundary conditions over the surface of this filament. Now of course, we want to be considering shapes that are changing probably pretty wildly in time, as kind of seen in that video. And so from a computational perspective, this quickly becomes way too inefficient to actually be prescribing boundary conditions over the entire surface of this filament at every time step. And so what's commonly done to simplify this problem is a very old idea dating back to the 1950s, which is just to do kind of the obvious thing and say, okay, the structure is very thin. Let's just approximate it as just a one-dimensional curve of point forces in the three-dimensional fluid domain. All right, and so to do that, right, we'll just take the fundamental solution for the Stokes equations, integrate that along the center line of the filament, right? So along with some force density F, right? Okay, and now this sort of very basic approximation, at this level, there's sort of nothing yet to tell the fluid that there's actually a three-dimensional structure there. So there's really nothing here that gives the filament any notion of thickness. And so to correct for that, some later ideas introduced later in the 70s and 80s were to say, okay, we want to tell the fluid that there's actually a three-dimensional object there. How can we do that? One way to do that is to say that, okay, we really want to impose that each cross-section of the filament is just moving with a uniform velocity. All right, now why might that be a sort of good thing to sort of tell the fluid that there's actually something three-dimensional in the fluid? Well, you can imagine that, okay, if the velocity field over the surface of the filament was non-constant, so looked like this, for example, then in the next time instant, you'd expect that, okay, then the cross-section would deform. In this case, it would get bigger. And of course, we want to maintain some notion of structural integrity of this filament over time, so we don't want that to happen. And so one way to prevent that from happening is to impose that over each cross-section of the filament, the velocity is as close to a constant as possible. And so to do that, what is commonly done is add a higher order correction, just in terms of derivatives of the Green's function for the Stokes equations. All right, and so that's done to cancel that leading order angular dependence over the surface of the filament. All right, and so this expression here is then an approximation to the fluid velocity at points away from the filament, right? And so if you actually wanted to use this expression to derive an expression for the velocity of the filament itself, you have to be a little bit careful because these expressions are actually singular on the actual center line of the filament. But doing an asymptotic expansion of this expression about epsilon equals 0, you can obtain an expression in terms of this sort of nasty looking local operator plus a non-local finite part operator that gives you then an approximation for the filament velocity given a force density along that filament. All right. And so it's really sort of this expression here that then gets, chopped up and put into numerical methods, right? So this is something that you can much more easily simulate, because instead of solving a boundary value problem, now you've just reduced your problem to this really a filament evolution problem that's only happening along a one-dimensional curve. Okay, so this method is very popular because it greatly sort of simplifies this filament evolution problem. But really there are some questions remaining about this expression. So in particular, what is this expression actually approximating? All right, so the question that I want to answer now is, so how close is this slender body approximation to some notion of a true solution, right? So this is, some approximate expression for the effect of the filament on the surrounding fluid. How close is it to a true solution? And the reason that this question is tricky from sort of at the outset is really that it's not clear how you would actually formulate this notion of true solution. Because, right, what we're given as data in this slender body expression is this force density F, right? And that's prescribed just along a one-dimensional curve. So we're given this data along a curve, and somehow we want to be able to solve for the surrounding three-dimensional fluid velocity as well as the velocity of the filament, right? And so it seems like there's sort of a dimensional mismatch here, like we don't seem to have enough information to actually have a well-posed boundary value problem, all right? And so the question that we have to start off with is, what are we actually approximating with this expression? All right, so, okay, to answer that question, I want to introduce the slender body PDE. So now I want you to think, okay, we have a three-dimensional filament, so there's actually some surface to this filament here. Outside of the filament, okay, we have our Stokes equations. All right. And now on the surface of the filament is where I want to prescribe some sort of funny-looking boundary conditions. All right. So the first condition is, okay, so we have our data F coming in here. And so this force data F, we're going to take that to be the total force per cross section over the surface of the filament, right? So we're just going to take each cross section of the filament, sum up the stress over the surface of the filament due to the interaction with the fluid. All right. So, okay, that force density is our total force per cross section. That makes sense. But as mentioned on the previous slide, that's not enough information to, be able to uniquely determine a solution to this problem. Right. And so in particular, we have to make use of this fiber integrity condition as well. So in particular, we want to strictly impose this condition that, okay, we don't know what the velocity at the surface of the filament is, but we do want to constrain it to be independent of the angle over each cross section. So in particular, we want the velocity of the filament to only be a function of arc length, all right, and not of the angle over the cross section. All right, and so with this constraint, right, so we have this sort of partial Neumann boundary condition, right, because we have sort of an average or a total force information, and we have this sort of partial Dirichlet boundary condition where we don't know what the value is, but we know that it has to, have some structure to it. All right, and so, okay, together, these two conditions, why do we think this is kind of the right way to think about slender body theory from a PDE perspective? Right, okay, so one reason, or one thing that this gives us, is a very natural energy identity. Right, so that's very useful because, okay, so if we just, take that PDE, multiply by U, integrate by parts, right, then we get this energy identity where, okay, on the left-hand side, right, we have our viscous dissipation, right? So the sort of the energy dissipated due to viscosity in the fluid domain. So our viscous dissipation is then balanced by where we would usually have boundary terms. Because of how we've defined our boundary conditions, this just reduces to an integral over the filament center line, right? And we get that our force data F is appearing then on the right-hand side. So on the right-hand side, then we get the power that's exerted by the slender body on the surrounding fluid. So the viscous dissipation in the fluid domain is balanced by the power exerted by the slender body. All right. And so out of this energy identity, then we get, you know, immediately existence, uniqueness of solutions, as well as a nice energy estimate. All right. So we can, in particular, given just that one-dimensional force data, we can actually bound the solution to this boundary value problem. All right. So that's all very useful because, you know, now we have a framework in which we can actually talk about, okay, what if we compare this solution to slender body theory? You know, can we quantify the difference? All right. And so there's one more sort of small, or actually not so small piece that has to be considered here in the well-posedness theory, which is, okay, we want to use this energy framework to get an error estimate for slender body theory. So we do have to be careful about this constant that's appearing in the energy estimate. All right, and so just to kind of go through that a little bit, right? So there's a bunch of inequalities that are sort of hidden in that energy estimate, and we have to just go through and carefully verify how those constants depend on the filament radius as the filament radius goes to 0. And so I guess the important one is really this quasi 1D trace inequality that we have bounding the boundary value along the surface of the filament by the velocity of in the fluid domain. All right, and so in particular, this trace inequality involves a root log epsilon dependence as epsilon goes to 0. So in particular, this inequality is blowing up as epsilon goes to 0. So that's something that we have to be aware of, you know, in doing this energy estimate or in doing the error estimate. All right, so this is something that we'll have to take into account. Just to summarize the well-posedness theory here, so we've developed a notion of true solution for the slender body PDE, or for slender body theory, right? And it satisfies this energy estimate with the root log epsilon dependence. All right, so we have this framework now, and now we can actually get to really kind of the full question, which is how does slender body theory actually compare to this notion of true solution that we've developed? All right, and so to answer that question, we have to use this nasty integral expression coming from slender body theory, which so I've written it out in a bit more detail here just to show there's a lot of terms involved. To compute, now there's two sort of residual error sources that come up. So in particular, there's some theta dependence if you just take this velocity expression and evaluate it on the filament surface, right? But we can show that, okay, the angular dependence over the filament surface is small, so bounded by epsilon log epsilon. And then there's also some error in using this expression to compute the total force per cross-section. But that error is also small, bounded by epsilon in particular. All right. And so combining those two error sources, putting them into our energy framework, we then can actually bound the difference between this notion of true solution that we've developed and the slender body approximation. All right, so in particular, the difference between the true solution and the slender body approximation is bounded by epsilon log epsilon times just that force data that we're giving it. All right, so in particular, it goes to 0 as epsilon goes to 0, right? All right, and then so this first expression is valid in the fluid domain for the bulk fluid velocity. And then if we want to look at the expression for the velocity of the fiber itself, right, then the difference involves an extra root log epsilon coming from that trace inequality. All right, but in particular, both expressions both expressions approach each other as epsilon goes to 0. All right. So from there, there's various ways to sort of develop the framework a bit more. You can consider free ends. That's a very sort of obvious question to want to answer because, clearly the filaments in the video at the beginning had free ends. But can show that as long as you have a radius that decays smoothly to 0 at the endpoints and you're giving it a force density that decays at the same rate as the radius, then you get an analogous error estimate. You can show similar things for fibers that have crazy shapes but are constrained to be rigid using slender body theory. And then you can consider sort of variations on slender body theory, such as the method of regularized Stokeslets. And then we also created a numerical method based on this slender body PDE using a boundary integral formulation of the slender body PDE, and we were able to sort of verify this convergence result numerically. But one sort of application or an extension, I guess, that I want to talk about a little bit more deeply is what I call the slender body inverse problem, which is not really, when you think inverse problem, not really the same thing as a true inverse problem. But what I mean by this is, okay, so far all of this has been about this sort of forward map where, okay, you have this operator taking the force density along the filament to the velocity of the filament, right? So you're mapping this force density to the filament velocity. And in that case, we showed that, okay, slender body theory is a really good approximation of this map, right? Taking force density to filament velocity. But, from a applications perspective, it's equally of interest to really want to know something about the opposite question. So, what if you want to prescribe the velocity of the filament and then compute the force density along the filament, right? So what if you want to try to use slender body theory to approximate this inverse map, taking U to F instead? So from a PDE perspective, this is actually really simple, right? It's just the Dirichlet problem for the Stokes equations. You just happen to be giving it Dirichlet data that's independent of the angle over the filament, right? So from a PDE perspective, everything's known about sort of the true solution. But really the difficulty in this question is the slender body approximation itself. So in particular, this operator, this slender body operator, where you have this long local expression plus this non-local finite part integral operator, turns out that it's not a good idea to actually invert this expression or try to, naively invert this expression. Right, okay. So, but I want to talk a little bit more about, or explore a little bit deeper, sort of the nature of this ill-posedness and talk about sort of, fixes that we can identify to remedy this. Okay, so I want to talk about this in a model scenario, a very useful toy problem for this, which is let's consider just a straight but periodic filament. So a straight filament with periodic boundary conditions at the ends. All right. And so, okay, this is a very nice geometry for this problem because we can actually explicitly calculate all the eigenvalues of this operator. So in particular, sort of the behavior decouples into the tangential direction along the filament and then the directions normal to the filament. All right, and so in particular, I want to study the eigenvalues of this problem here. So where we take, right, so the eigenvalues satisfying, okay, total force over the surface of the filament equals lambda times the filament velocity. All right, so we want to find those eigenvalues lambda. And so for the PDE problem here, which I've written down, we can explicitly calculate what those are. In the tangential direction, we get this expression. In the normal direction, we get another explicit expression. In both cases, they're pretty nasty ratios of modified Bessel functions. But we can, I mean, Bessel functions are really nice. They satisfy a lot of really nice properties. So we can show some really nice things about these expressions. In particular, okay, in both the tangential and normal directions, these expressions just grow linearly in k, so linearly in the wave number k. So really, so morally, this velocity to force map along the filament is really very much like just like the usual Dirichlet-Neumann map along, along a surface, right? And so, okay, but what if we try to use slender body theory to approximate this map, right? So again, in this geometry, we can calculate the eigenvalues of this velocity to force map in both the tangential and normal directions. And in both cases, right, so in both directions, we have a plot here of what those expressions look like in red, plotted versus the PDE eigenvalues, which are along the blue, right? So the PDE is growing linearly in k, and actually in both the tangential and normal directions, we have blow up in the eigenvalues at some finite k. So when k is proportional to 1 over epsilon, so these sort of high wave number instabilities. Okay, so it's not going to be a good idea to just naively try to invert this slender body operator, but we can consider some different ways of regularizing this operator. All right. So one thing that we can do is just, okay, in this model geometry, we have an explicit Fourier series representation. We can just try truncating the Fourier series at some, finite wave number in both tangential and normal directions, right? So we can kind of capture the agreement at low wave number and then, ignore everything that's happening, at high wave numbers. Right, and so this is really, okay, we can only really explicitly do this for this model geometry, but what this does is mimic the effect of numerical discretization, right? So you're just, when you discretize for numerics, you're sort of really chopping off, you're fixing some, h where beyond which you're not resolving, so or below, some length scale below which you're not going to resolve what's happening. So this is kind of mimicking the effect of numerical discretization, which is how this operator is going to be sort of used in practice anyway. And then another regularization that you can consider is what I call the delta regularization, which is just to take that finite part integral and insert instead a small parameter so that it no longer has to be considered as a finite part integral. Okay. And so for that delta regularized operator, you can again explicitly calculate the eigenvalues in this geometry. And instead of blowing up at a finite wave number, okay, we just approach some asymptotic bound at high wave numbers. So in particular, they're only diverging linearly as k goes to infinity. Okay. And so for both of these regularizations, then you can show that, okay, both of these then, if you consider the regularized versions of this slender body operator, then you can get a good approximation of this inverse map, of this velocity to force map along the filament center line. So in particular for the truncated operator, given a sufficiently regular velocity of the filament, you can get epsilon squared convergence. And then for the delta regularized one as well, you can get this epsilon squared convergence, plus a little bit of information about how to best choose this parameter delta. Okay, so from there, I want to kind of segue into, all right, all of this has really been at kind of a fixed snapshot in time and really trying to understand this force to velocity map along the filament, or velocity to force map along the filament. And so now I want to talk about, okay, we have this sort of picture, really a picture of what's going on at a fixed time instant. So now what happens if we want to actually consider the filament evolution problem? So the filament is actually changing its shape over time, like in the video we saw. All right. So okay, what's kind of the dynamical picture that I have in mind? All right. So now to consider the dynamical formulation, right? We're just going to consider no slip boundary condition. So this velocity at the filament surface is the velocity of the filament, right? So we can consider that as dx dt, where x is the centerline position of the filament. All right. And so now what we want to do is give it kind of a sort of physical forcing along the filament. And so to do that, we're going to use Euler-Bernoulli beam theory. Right? And so what that really is really just a very simple elasticity law. So really it's that the filament wants to minimize its curvature coupled with an inextensibility constraint. So the filament wants to not be curved, but also wants to keep the same length over time. All right, so that's really all this is saying. All right. Okay, so putting that force density into this force to velocity map, right? Then we obtain a filament evolution problem, right? So we have dx dt equals, and then we have this slender body, force to velocity operator that's taking now this Euler-Bernoulli beam expression, right? And so we have this now filament evolution problem that we can study. All right. Okay, so we want to study this problem, and one way to kind of get a sense of what we can kind of expect from it is to just consider local slender body theory. So this is slender body theory without any of the integral terms. You just ignore the integral terms in slender body theory. Then you just get a very, very simple approximation of this force to velocity map. So it's, it's not very accurate in the sense of the previous slides, but we have this very simple expression that's really just a matrix multiplication that's taking the force density then to the filament velocity. And so using local slender body theory, you can say everything you want to really about this filament evolution. And so in particular, it evolves so the evolution is really just like a fourth order parabolic evolution. And you can even consider giving it some kind of internal forcing in the form of a preferred curvature and say things about, what preferred curvature is going to make the filament swim, right? So, this one moves forward, makes some progress. And, what sorts of internal forcing are going to just cause the filament to just flop around and not actually go anywhere. So that's what that one does. Okay. But that's all just using local slender body theory. And so really the real question that I want to consider is, what if we use this notion of sort of true solution, this true force to velocity map that we've developed to consider this filament evolution? I mean, so to get there, right, we need a lot more information about the mapping properties of this operator taking force to velocity, right? So the strategy is really going to be, we want to, since we know everything about this straight but periodic filament, we want to use that to try to say something about what if we have more general curvatures, right? So we want to be able to say something about what if the filament has, any kind of curvature. Okay, so we want to take the info that we have from the straight but periodic filament and use it to understand the curved filament. And so today I'm going to be talking about a toy problem for doing this, which is the slender body Laplace equation, right? And so it's really just the same type of boundary value problem, but just for the Laplace equation, right? So we, in particular, now we have, instead of a total force per cross section, we just have, total Neumann derivative. Total Neumann boundary value is this density F, and then, U is independent of the angle over the cross section. All right. And so in the in the Laplace setting, you can also explicitly calculate the behavior of this F to U map in the straight but periodic setting. It's just given by a Fourier multiplier. That's again a ratio of modified Bessel functions. It's a little bit simpler to work with though. Okay, and so some things you can say about that Fourier multiplier is that we know all the mapping properties basically because we have an explicit Fourier multiplier, and we can use that to say that if we have a filament with more general curvature, we can decompose this F to U map along the filament as a piece that, so we can take out the straight piece, so the same where we know everything that we want to know, we have an explicit expression, plus two remainder terms, one which is small in epsilon and one that's more regular. All right. And so this is something that we can explicitly do in the Laplace setting using a layer potential representation of this slender body PDE. So in particular, you can express that F to U map or U to F map using layer potentials, so single and double layer potentials as written here. And then using that, we can mostly explicitly calculate things in the straight periodic setting. Then we can obtain sort of a decomposition of this slender body U to F map, this slender body Dirichlet-Neumann operator. All right. So then where is this sort of heading? Well, the hope is that the same thing can be done in the Stokes setting as well. So taking where the Stokes slender body F to U map and decomposing it in the same way. And so hopefully we can then obtain an expression for the filament evolution in a similar form where we have this decomposition with the straight operator plus these two remainder pieces. And then hopefully using that, be able to establish local well-posedness, at least in the case of a fiber that is allowed to grow or shrink over time. And then sort of a much more challenging question is actually enforcing this inextensibility constraint, which we do want for physical purposes, but it adds a bunch of additional analytical challenges. So there's certainly questions there to be answered. And then sort of really one of the major goals of this program is to actually be able to obtain this slender body PDE formulation as in the limit of an actual 3D elastic body, right? And so from there be able to really establish a full hierarchy of models going all the way from 3D elasticity all the way down to just this very simple local slender body theory expression. Okay, and so with that, that's the end. So thank you.
Thank you. Are there questions in this talk? About the slender structures? Usually we hear about the slender beams. Now is more difficult, more biological, the setting. There is a conference about thin structures in Naples.
Oh, really?
In September,
Oh.
the usual one. Any comment? If not, we thank again the speaker. So I introduce the speaker, which is Francesco Grotto from the Scuola Normale Superiore University of Pisa.
Università
Now
di...
University.
Yes,
Okay.
yes, the affiliation was incorrect in the form, unfortunately.
Okay. Please, go on.
Thank you so much for the invitation. I think this was a incredible week with a lot of very interesting contributions. Yeah, so Laurel took a bit less time than an hour, and I think I am also going to do so, since we are all a bit tired. So I will not be going through many technical details, and just try to convey the main ideas of two works, actually. So the first is a work of last year I did with Umberto Pappaletta, so that he partially contributes, even if unfortunately he could not be here. And the second is more recent, with Marco Romito and Milo Viviani, and you can find it on archive. I posted it a couple of days ago. All right, so luckily, Franco already introduced most of the objects I'm going to talk about. Still, let me do a bit of a recap. So yeah, so now it is my turn to have Euler equations on the screen. I will be considering only 2D fluids, incompressible. And the domain is not really important for what I'm going to talk about. You can consider smooth bounded domains. It is a bit inconvenient because of boundary conditions, so let us just think of a full plane. But everything I'm going to say stays true on the periodic torus, the two-dimensional sphere, and like more generally closed surfaces. And right, so the PDE is the familiar one. You know, I always consider it in the form of vorticity, since I'm going to talk about point vortices. And so the equation takes the form of a nonlinear transport equation, and the vector field that advects the vorticity omega is given by Biot-Savart law. So since I will be sticking to the case of the full plane, the green function is just a logarithm, and the velocity field is given by the convolution of the vorticity field with a very simple vector field, like x orthogonal over x squared. All right. So what are point vortices? It is an ODE model, actually, that produces a very weak solution to Euler equations, in which at each time the vorticity field omega is concentrated at finitely many points on the geometrical domain. And those points are state points, they stay delta Diracs, and they are carried around, they are advected by the vector field generated by all the other vortices. Right, so here it is a picture just for the intuition. So each of the vortices, they are blue and green, since they can have positive and negative intensity, and according to the sign of their intensity or circulation, they will induce a clockwise or counterclockwise vector field around them. The thing is that each of the vortices does not feel the advection of its own vector field, which would be singular at exactly its position, but they just feel the vector field generated by all the others. So the resulting velocity field is just a superposition of all the generated velocity fields, but each of the vortices is dragged around by the combination of the vector fields of the other vortices. Right? And this is important. It's important because often in this kind of models, one is misled and confuses the dynamics perhaps with Coulomb dynamics that are second order. They have the same kind of interaction, logarithmic, but they are different in the substance. And yeah, so this is the ODE system, and as I was saying, it is singular, and this happens because of the singularity of the interaction potential. So I will use this complex notation for points on the plane. This turns out to be very convenient in order to keep notation compact later on. So please identify points of the plane with points of C. Anyways, then the analysis is all real, of course, and so derivatives are to be thought as real, not holomorphic derivatives. But it is just a notation thing. And so, right, so this is the ODE system. It is singular, meaning that when two positions of the vortices coincide, the vector field is not defined. But luckily, from a physical point of view, this almost never happens. And so there are, this was one of the first, but there are many generalizations of this kind of results saying that for almost every initial configuration of the vortices, the dynamics is well posed for all times, meaning that they do not collide. And as long as they do not collide, of course, the vector field is smooth, and so also solutions will be smooth. Still, yeah, okay, no, sorry. This is, yeah, just let me quickly go over this also. In what sense vortices satisfy the Euler PDE? You see, the two-dimensional Euler equation do not have a regularizing effect, so there is no Laplacian. So you need a rather weak notion of solution, but you can interpret them this way. You write a weak formulation in this form here. So here is the Biot-Savart law that gives that produces the velocity field advecting vorticity, and point vortices, the dynamics of point vortices satisfy this formulation in the sense that if you look at this integral here on the right hand side, interpreting the vorticity field as the empirical measure of point vortices, well, you can regard this integral as evaluating this singular kernel at points. Of course, this kernel is going to be singular when x coincides with y. So yeah, so this is the caveat. In order to have this formulation of the PDE, you need to remove the diagonal term of this double integral. But with that being said, the PDE is satisfied, and even though I will try to argue that this kind of weak notion is extremely non-unique, it is useful to interpret the fluid dynamic motion for this kind of system. More generally, anyways, the system is very old. So it was first introduced by Helmholtz in the 1800s, and it is interesting not only because of its relation with fluid dynamics, which is I'm mostly concerned of, but I want to mention this. It is an Hamiltonian system. I will write to you the Hamiltonian in a moment, and so it is a very relevant example of a singular Hamiltonian dynamics. And there is a huge literature on that aspect of point vortices that I'm not going to talk about, but it is important to keep that in mind. All right. Anyways, yes, another way to see that this kind of weak formulation is satisfied is to take the approach of many works of Marchior and Pulvirenti approximating the Dirac deltas with patches of vorticity, meaning indicator function of areas of the plane. And in L infinity, the PDE is well posed, so those are proper solutions to the Euler equation, and you can send them to the limit converging to point vortex dynamics. Yeah, sorry. All right. No, doesn't work like this. Yeah, more or less. Anyways, as I was mentioning, the system, the ODE system is Hamiltonian. The Hamiltonian is simply the interaction energy. So here I'm going to call it H. Yes, it is Hamiltonian in these coordinates, in the components, first and second components of the positions. Yeah, multiplied by the intensity that has to appear somewhere. But anyways, the Hamiltonian is one of the first integrals preserved by this system. It corresponds to the energy of the PDE, while the entropy is represented by the sum of intensities, which of course is conserved since the dynamics do not involve intensities, they are just preserved. And other first integrals being the moment of inertia, which is the sum of square distances, weighted with intensities, and the center of vorticity. All right, so having these first integrals, at least when we have a very small number of vortices, just 3 of them, on the full plane, the system is integrable. Well, you might question, but no, yes, so 3 vortices means 6 degrees of freedom, and like this is a vector, so there are 4 first integrals. There's too many, yes, they are not in involution, but still, you can integrate the system, only not just with this set of first integrals. You need to take a combination in order to have first integrals in involution. All right, and there are important symmetries of these systems, of the system. I mostly care about 2 of them. So that are symmetries that allow me to reverse time in the dynamics. So the first one is a change of sign in intensities. This makes it so that every vortex is now generating a vector field on the opposite direction. So the whole dynamics reverses. But another way to do so is to take complex conjugate of all positions. This is flipping the plane upside down, and this corresponds to flipping all the circulation directions. So it is equivalent. And I will be using this a lot. Why so? Because even if I told you that almost all configurations do not lead to singularities to collapse, from now on I'm just going to talk about collapses. So, right, and from the very beginning of the theory, in the 1800s, it has been known that vortices actually can collide, and there are specific examples of configurations in which they do so. So for 3 vortices, actually the dynamics is integrable, so you can characterize configurations leading to collapse, and I will do so in a moment. But here it is explicitly an example of evolution of vortices leading to collapse. If you just take this Zj as the position, this is a function of time, starting from positions Aj, and the time dependence is given by this common function R that you can see is as t goes to 0 from the left, is making the position smaller, so they are coming closer and closer to the origin of the plane, and then there is this oscillating factor that makes them spin faster and faster as they get closer. So if the dynamical parameters you see here, B and A, satisfy those relations down there, this is a true solution of the ODE system, and it is what it is called a collapse of vortices. So as t arrives to 0, the 3 positions will coincide, and I mean it is not trivial, because you see the vector field is becoming increasingly stronger, and so in order to produce such a configuration, you have to finely tune the position of vortices so that the vector field cancel and they are getting closer and not just sped up to infinity. Okay, so once you have a collapse, by reversing time with the symmetry I told you, preferably the conjugate symmetry that does not change intensities, you can produce a burst of vortices, right? So if you take that symmetry, what's happening is that now from a single position, vortices are spinning outwards. So you are splitting a, say, single vortex into 3. And this is the picture. So this is a picture that I think many people have seen, because it is in the classical book of Marchioro and Pulvirenti. All right, so, and and you can interpret this as both a collapse or a burst. Okay, so what I'm going to talk about is I would say, a twofold result. First, I'm going to try and explain to you how you can actually produce a huge variety of these collapses and bursts of vortices. Namely, in a large configuration of vortices, one can split one of them always. So actually, this kind of singular solutions are very present in the phase space of the system. They have zero Lebesgue measure because of the theorem of above, but there's really many of them. They cover entire submanifolds of codimension 1. And then, once I have told you that you can split and collapse arbitrary number of vortices, I will discuss what should happen after the collapse. Because you see, when the ODE system stops to have meaning, one might wonder, well, what is the physically meaningful continuation of the dynamics? Like this is an idealized system. So in the reality, there are no point vortices, of course. And as a model, one should wonder how it stays physical after this mathematical singularity of the model. Okay, so a couple of references. So this is the work of Umberto on splitting and making vortices collapse in arbitrarily large configurations. This here is a work on continuation after a collapse, but as a general reference, I want to mention a survey paper. This is a very nice survey by SNRF, covering also Hamiltonian aspects of the point vortex dynamics, and this is a very nice book that is also very focused on the numerical application of point vortices in simulating two-dimensional fluids. Okay, so let me start from bursting vortices, bursting 3 vortices out of 1 in a single, in a large configuration. So this is the result. Let me first read it to you, and then I will discuss it a bit. So let's say we start from a large configuration of vortices, n vortices. I don't care about their positions. I don't care about their intensities. What I can prove is that if I have this configuration at time 0, I can produce a solution of the point vortex ODE system with 2 more variables, so n plus 2 actual vortices, 3 of those n plus 2 vortices starting from the initial position of each of the vortices I had at time 0. So I can actually produce a true solution of the ODE system in which I split one vortex in a large configuration. And this also means that by inverting time, I can produce arbitrarily large configurations in which 3 vortices will collide into one at finite time. So this really populates the phase space with singular solutions. By the way, this holds in any of the geometries I mentioned to you, and as a byproduct of the proof, it also holds that there is a collapsing and bursting solution of 3 vortices very close to a self-similar one in all of those geometries. And this is because the proof is essentially by a perturbation approach. So here is a picture for your intuition, starting from many vortices. I can split one of them. And notice that I have split a red vortex into 2 blue and 1 red. And this is because, and I will detail it a bit more later. Any of those splitting or bursting solution needs to preserve the total vorticity. So I cannot create vorticity out of nowhere. The total sum of the vortex intensities has to stay the same. Otherwise, I'm not able to compute the solution. When I do so, before I move to the proof, what's happening? Well, let us take a look at one of the, or perhaps the most important observable of the system, the energy. Why so? Well, because there are many reasons to be interested in point vortices, but I believe that one of the main ones is that they were invented as a discretization of the fluid, and so they might be used as building blocks, for instance, to build a singular solution, since they have this weird behavior when they collide or when where they burst. So what is happening to the energy? Usually the energy controls this kind of weird phenomena, right? What is happening to the energy? Well, when they merge, or rather when they collapse, since the energy is made of pair interactions, we are losing some pair interactions, and so the energy is decreasing. Total vorticity is conserved, but the energy is decreasing. On the other hand, if I split a vortex, I am increasing the energy. So in principle, one might use the theorem to build a solution of the point vortex system in which they split, and maybe they split very, very fast and very, very often, and the energy is increasing, but globally omega, or rather, the entropy is preserved. Unfortunately, I am not able to prove a theorem saying this. I would be very happy to do so, but I can't. I am not able yet to prove a theorem in which I say that such a system in which vortices split converge to, say, a solution in LP of 2D Euler equations with this behavior. Anyways, how does one prove the theorem? Well, the idea is to reduce to a perturbation argument in the following way. So perhaps I have a picture. No, I don't. But anyways, the idea is the following. Let us just choose one vortex and just look at that and think of all the other vortices as very far away. I mean, by scaling, this is not a problem. And so the system, rather the dynamics of the single vortex Zj is the following. Is seeing if I am to make him burst, the resulting vortices will only see the influence of the other two very close by, and the rest of the configuration will just act as external forcing, which is going to be regular. Here I'm writing that the forcing has this kind of regularity, not because I want to be fancy, but in order to motivate the fact that if I carry on with my program, not only am I able to discuss many vortices, but also, for instance, boundary effects. So yeah, so when you're far away from the boundary, you can model the boundary effect by this kind of forcing. And of course, yeah, I did not write to you the vortex equation in a bounded domain, but what happens is that in order to realistically describe the effect of the impermeable boundary, there are not only not only pair interactions of vortices, but also a self-interaction modeling the distance of the boundary. Anyways, let me start to discuss this kind of perturbed vortex system. And if I am able to prove that there exists a point vortex burst or collapse under this external forcing, then I can conclude the proof with a larger fixed point in which I say, okay, so first, the the iteration scheme for the fixed point is the following. I make the three close by vortices evolve self-similarly, and then or close to self-similarly, and I let the other ones evolve as the vortices were not there. And then in the next step, the forcing of the closed vortices will be given by the evolved large state outside. And this will actually converge if I get sufficient a priori bounds, which are a consequence of the stability I needed to discuss in order to solve this very equation here. All right, so how do you solve this perturbed system? And again, the idea is another fixed point in which one has to be careful. So this was really the technical core of the argument. One has to properly choose coordinates for the system centered in some way around the self-similar solution, so that linearizing the system around in these coordinates around the self-similar solution, it is easier to discuss the stability of the system. If you try to do this in Cartesian coordinates, you fail miserably. So one has to be careful because as soon as you start linearizing, the computation becomes untreatable otherwise. And you can tell I am centering everything around the self-similar solution because, you know, if you remember, I wrote the self-similar solution as initial position times a time-dependent object, and the AI were the initial positions. So since the solution is self-similar, those ratios AI over AJ describe the initial triangle, and these ratios, difference of ratios, measure the distance from this self-similar solution. Okay, so yeah, and actually it is exactly those differences that measure that distance, and so one is especially interested in linearizing in this coordinate that I call x. So I cannot write the linearization matrix because like even on the paper it takes 1 page and a half, so let me just say it is a matrix, but it is a 4x4 matrix, and so you can compute eigenvalues, or rather you can produce estimates on the eigenvalues. And it happens that if they are all negative, and this is a condition that you can tune properly choosing the initial positions and intensities, well, you have enough stability to perturb the self-similar solution and obtain a solution of the perturbed system. And what we did, we made a choice. We chose, yes, there should be a minus sign here, sorry. I told you that they cannot have all the same sign. One of the three vortices has to be negative and the other two positive. But yeah, we chose proportion 1/3, 1/3, 2/3, 2/3. So yeah, with the sign minus, they sum to. They sum. Yeah, there is a minus here, minus sign. It's not really a minus sign, sorry. Yeah, okay. Minus. All right. And then we had to finally tune positions. We wanted to at least exhibit one configuration, and that in the end was done by hand numerically. But as soon as you have one, since the condition on eigenvalues is open, you have a neighborhood, and so, yeah. All right. So now that I hope I have convinced you that you can always split or collapse vortices, what happens after a collapse? So, yeah, in order to study such a singular phenomenon, I think natural idea is, okay, so let us regularize the system in some way, and then send the regularization to 0 and see what is the limit. Hopefully the limit will not depend on the regularization procedure I have chosen, and this will identify the correct physical continuation. This is not the case. Unfortunately, this is not the case. And I will show you two different regularization procedures that I believe are very natural in this context, that produce completely different results. So, yeah, right, okay, let me perhaps first just spend a few more words on the weak notion of the PDE. As I said, that weak notion is wildly not unique. Measured value solutions are of course wildly not unique, and with the, of course, I mean that inside of what I showed you, you can take vortices, you can make them collide, and then you can let them stay coalesced for later times until some moment I decide in a completely arbitrary way in which I split them again. So, of course, I can do whatever I want at this point with this system. Completely not unique. And so, yeah, so already in the first works of people discussing this weak formulation, Laurel and Choquet, you can see expressions as wildly non-unique solutions. And yeah, so the picture is the following, right? So after a collapse, you get one single point whose intensity is just the sum of the previous intensities, and I can decide to keep it one vortex still, is not interacting with still, or to make it burst at any time I want. And then burst them again, of course. All right, so let us see. How do I study what is happening after collapse? Here, I need to spend a few more words on what can be a collapse configuration. So, right, so in the remainder of my discussion, let us stick to the case of just 3 vortices, because it is the paradigmatic one. Because of conserved quantities, 2 vortices can never collide. This is because the Hamiltonian is conserved, and for 2 vortices the Hamiltonian is just logarithm of the distance. So 2 vortices can never collide. 3 and on, yes, they can. Okay, so but let me stick to the case of 3 vortices, and here the deterministic system is integrable. So I will be perturbing a integrable system, and yeah, so to those of you that know about Kornogorov-Arnold-Moser theory, this rings a bell. And of course, there are people that attempted to study this this system with CAM theory. But okay, this is a story for another time. And so yes. So what about the characterization? Yeah, just take 3 vortices, positions z1, 2, and 3 at time 0. What happens is that the maximal interval of the solution, I mean, if they are distinct, the solution will exist for some time. The maximal interval of solution can end with a collapse, or may be starting with a burst at an earlier time. But for 3 vortices, this can only happen if the motion is self-similar. So if the positions form a triangle that remains similar with itself at all times. And I have 2 conditions that characterize exactly when this happens. So you need to have this first condition on intensities. The sum of all double products has to be 0. And then I have a condition on the moment of inertia, which I recall to you, it is the weighted sum of the distances squared. If both are satisfied, then the solution is self-similar. And then it might not be a collapse or burst, it might just stay an equilateral triangle rotating, and this is called the relative equilibrium. I will not be discussing that today, but you can also cover it with the regularization procedures that I described below. All right. Let me open these conditions. So yeah, so this condition here is the one of on intensities, I will be fixing intensities. So let us say they are proportional, as I told you in the theorem of earlier. And then I have a condition on moment of inertia. Fine, that has to be 0. But then I have some freedom. I can choose the center of vorticity and the level of the Hamiltonian. Okay, the center of vorticity, I choose it to be 0. So I center my configuration in 0. And then if I want to study where to start self-similar evolution, I don't care if they are very close to collapse or not so much, because it is self-similar. So just to study the configuration, I can fix one intensity to 1 and scale the others accordingly. All right, so this reduced a couple of degrees of freedom. And now what I only care about is the ratios of the side of the triangle. So for instance, I can write these conditions only in terms of this variable z, which is the complex ratio between two of the positions. Okay, so in order to concretely see what are the correct configurations collapsing, I have to impose the condition I equals 0 and the Hamiltonian equal to a certain level. That only depend on z. So here is a picture. Yeah, perhaps there it's more clear. So the green line is the level of the moment of inertia. Of course it is, because it is an ellipse and it was a quadratic condition. And the other black line is the Hamiltonian level set. Yes, this perhaps is a bit misleading. I have chosen a bad picture, but it is almost touching, but it is not. There are two intersections in this picture, and I remember to you, this picture is in the plane for z, the ratio of two sides. So the intersections characterize classes of self-similarity of the collapses, and conjugate points marked with C and B correspond to inside the same similarity class in this case to a collapse or a burst, because I told you if I conjugate everything, I reverse the dynamics. But this is not the only picture. Here I have two intersections. If I change a bit, for instance, the level of the Hamiltonian, I can enlarge the black level set and make it intersect the green level set 4 times. And so these will be different similarity classes. All right, so with the same level of the Hamiltonian, I can have more similarity classes for collapse. Fair enough. What does this have to do with regularization? I'll show you. So let me first do a deterministic regularization of the system. I just regularized the interaction kernel, which was singular, so now the system is well posed. And if you look at the regularized system, what happens is that, when epsilon is very small, they kind of rotate and try to collapse self-similarly, but at some point, instead of collapsing, they become collinear and then they open again. So they are not collapsing. In the limit, which is unique in this case, the continuation after collapse which is selected is simply the collapsing solution reversed with the conjugate. So I told you that conjugating everything, I can reverse time, and the deterministic regularization selects exactly that solution. First, I make vortices collapse, and then they open again with their positions being simply complex conjugated. So the deterministic regularization likes a very precise trajectory in the z-plane. Oh, come on. Yeah. So starting from a collapse before time 0, I move to a burst, and vice versa. All right. But then you can regularize it in another way. You can add Brownian motions to the dynamics. So as Franco was saying, this makes it so that vortices never collide. I mean, almost surely with respect to the noise, but whatever initial configuration. So you can feed this stochastic dynamics the collapsing configuration, and vortices will almost surely never collapse. And why is this a reasonable choice? Well, I mean, it is a simple choice, and it is isotropic, so it does not have a preferred direction, so it is a first natural attempt at regularizing. But also, if instead of, yeah, so here I am only taking 3 vortices, but if they were many, I could consider a scaling limit in which this point vortex system, or rather its empirical measure, converges to Navier-Stokes equation. So I would argue that this is a rather natural way to regularizing the system. All right, and then I want to send the regularization to 0. So what is going to happen? Well, for sure, at least in that very weak sense of solution, I am converging to solutions of Euler equations. So the law of the process when epsilon goes to 0 will be supported by solutions of the point vortex system. Inside of the pictures I showed to you, this does not say much because, I mean, there are many possibilities of bursting. And the deterministic regularization only chooses one. Anyways, this you can prove that the limit will still be solutions of the point vortex system, and moreover, they will have the same level set of the Hamiltonian. So the continuation of the dynamics preserves the Hamiltonian even in the zero noise limit. This is a consequence of the fact that if you write Ito formula for the Hamiltonian, it is a local martingale. All right, but what is happening concretely, like where is this law, limiting law supported? Well, let me show you a picture. So this is a picture. This might look deterministic. There is no wiggling due to Brownian noise. Well, there is, only it is very small. This is a simulation with epsilon being 10 to the minus 10. And you can see that after collapse, they reopen. The triangle is similar to the one of before, but it is rotated. So I am not in the solution selected by the deterministic regularization procedure. Here I show you the same dynamics in the z-plane. I have moved from the collapse configuration to the bursting configuration, and this is striking, I think. The stochastic system moves very, very closely to the level set of the Hamiltonian. So conservation of the energy is very strong. It actually resists the stochastic perturbation. Much more than the conservation of I mean, the picture here is misleading. You might think that the system is moving the moment of inertia very much. No, I have scaled so that you can distinguish the lines. But of course, when epsilon is very small, invariant quantities are not perturbed much. All right, but worse can happen. So here I start from a rectangular triangle, and afterwards I still have a rectangular triangle, but the starting configuration is on an energy level allowing more intersections. And so this is one sample doing almost the same thing as before, moving from C1 to B1 in the same similarity class. But here is another sample. And here the similarity class has changed. So the zero noise procedure can select a different similarity class. And in the z-plane, this corresponds to moving like this. Right? So these are similar, but I am moving from a collapse in one class to a burst in another class. So the situation is a bit wild. And at this point, right, so for a long time I thought, okay, there are many possibilities. since the noise is isotropic, the limiting law will be uniformly distributed among all the possibilities. And we were not able to prove that. We tried it for quite some time. But then we decided, OK, so let us run a very precise numerical simulation. And so we ran, for many starting configurations, I think like 20,000 samples at epsilon equal 10 to the minus 10 with a very precise integrator. So we wrote what is called an adaptive integrator. It is a numerical integrator that slows down when the velocity field or the driving vector field is increasing in intensity. So we are not accumulating much error. And what we observed is that after the collapse, similarity classes are chosen uniformly at random. So if there is only one similarity class, well, it will stay in that class. But if there are two, well, it is 50-50. And it really is a 50-50. You can run a statistical test. The p-value is very high. It is really 50-50. But then the rotation angle after collapse, which means that, OK, so the collapse happened at minute 1. I look at minute 2. If I were to do the deterministic regularization at minute 2, I would see the same triangle just swapped, right? No, here I see it not only swapped, but also rotated with a random angle that does not have uniform distribution. And here you could ask, well, what is this distribution? And the fact is that the system is so unstable that even numerically, even going well beyond epsilon and approaching machine error, the empirical CDF of the simulation is not converging, is very widely oscillating, even if a huge amount of samples. And so what we are able to say is that the solution is not uniform in the rotation angle. The zero noise limit is not uniform. But I believe that the limit of these probabilities as epsilon goes to 0 might not be unique. And so these numerical oscillations are due to a superposition of different states that at the moment we are not able to characterize. So so let me conclude with a few pictures. This is the empirical cumulative distribution function of the angle for the case of one similarity class. And you can tell that, OK, so red is the uniform CDF, and there is a rather striking deviation. I don't know if you can see. So the solid blue line is the empirical CDF. It is not smoothed. We run a very large number of samples. And the small dotted lines is a confidence band of, I think, 95 or 99%. Which means that the approximation is very good, and so this is evidence that the distribution is not uniform. In the case where two similarity classes are present, you can see an even larger deviation from uniformity. So here is OK. So now, in order to write the CDF in this case, you have to divide the classes. So I have one plot for one class and one plot for the other. And in both cases, you can see that distribution is not at all uniform.
This is for fixed epsilon?
Yes.
Okay.
Yes, because as this is still, OK, so in order to be consistent in my presentation, all the plots I put in the slideshow are for epsilon 10 to the minus 10. We went beyond. We went up to 10 to the minus 14. So machine error is minus 16. And yes, so at all epsilon, it is very clear that it is deviating from the uniform distribution. It does not have a clear correlation with the angle, with a single angle selected by the deterministic procedure, meaning that it might be the peak of the PDF might be close or it might not. It oscillates in epsilon, and so I cannot extrapolate in epsilon, and thus I can only conclude that it is not uniform. And so I believe that yes, I believe that we need much finer control in order to understand better this limit and the continuation after collapse. All right, thank you so much.
Are there questions or remarks?
Is there evidence of collapse in situations where you have more than 3 vortices?
I mean, I can produce them, or rather, I can abstractly produce them. I can provide a very precise numerical approximation. Explicit configurations might be available, but not in the plane geometry. I believe people did the computation of the sphere. I have to look in my folders. There's people that spend their whole lives in studying this kind of configurations, but no, on the plane I can't. Not even self-similarly.
More questions? If not, we thank again the speaker. And since we are at the conclusion of the talks, on behalf of the editorial board of the Riemann International School of Mathematics, I would like to thank all the organizers for the nice work they've done, and all the speakers for the high scientific level and the enhancement of the subject and the good presentations. Concerning this fact, I remind that usually the lezioni leonardesche invite the speaker to contribute to the Milan Journal of Mathematics with some article, which could be either a survey or an original paper. This is in the aim and scope of the next one, please, of the journal. And we extend, due to the high scientific level of the meeting, the invitation to the speakers of this successful 7th RISM school on exotic solution and well-posedness for ODEs and PDEs. We will appreciate if you can send articles. You have time, you will receive instructions, and this possibly will produce a lasting testimony of this successful school. So thanks again to everybody, and enjoy the social trip. So you can clap. And last but not least, I know that Luigi would like to, is wishing to appreciate. I leave the floor.
Yeah. Okay, Franco already said a lot, so just let me add, as the only organizer left, a few words, and let me thank really all the speakers, in particular Dallas and Franco, and I think all these lectures have been fantastic. Personally, I also learned a lot, and I thank you all also for the participation, and let's enjoy the social event of this afternoon. Thank you.